Hello, good morning. Welcome to NASA System-Wide Safety Software Systems. We'll start off with Bob Pierce, AA for Aeronautics Research Mission Director.
Thank you so much, Joe, and welcome to everybody to this important meeting that's sponsored by NASA System-Wide Safety Project on software and systems V&V capabilities transfer. I just want to spend a few minutes, talking about a little bit about the big picture here. I think the future, as I think everybody online here knows, is much more dependent on software, and especially higher levels of automation and moving towards autonomy as we look to the future. And so the opportunity, the ability to verify and validate these systems is going to be increasingly important. And so making sure that as we make these advancements, we get them out to the practitioners, and we get their use in our processes and so forth, so that we can continue to develop even more advanced methods for V&V. And I think this also couples with the overall vision for a system that is more prognostic, and where we are ensuring the safety of the system, even with the introductions of new technology. So the ability to really understand where hazards and where risks are entering the system and being able to mitigate those before they become incidents and accidents, I think is increasingly important. And I think, and what we're doing here in system-wide safety couples nicely, I think, with advancements we're doing in airspace operations. And all of that having a backbone of higher, more information, more digital data, and so forth, which requires more sharing of that information, so it's available to do these kinds of prognostic analyses and so forth. And so I think the notion of higher levels of automation, not only for operation but for for prognostic safety management is absolutely part of the future. And so again, I think the work being done here to advance our V&V methods, even as automation continues to rapidly advance, I think is absolutely critical. And I applaud everybody that's working in this field, and doing the important research that is already leading to improvements, and not just the speed and efficiency in which we do the V&V, but obviously to making sure that systems really are safe and safer as we look to the future. So this is a really important conference. It's a really important meeting, and it's a step, an important step as we continue to do this research, pursue this research, pursue advancements in these tools and techniques, and continue to get these out to the practitioner, so that we can continue to build on them. So with that, I hope everybody has a very productive meeting. This is just to close, this is a really critical part of our portfolio. Without the work that's being done here, we don't have the basis, we don't have the foundation upon which to build a lot of our other research. So what you're doing is absolutely critical, and my hat's off to all of you. So with that, I will turn it back over to the organizers and to the System-Wide Safety Project and Misty and everybody, and again, wish all of you the best.
Thank you very much, Bob, for those remarks. I'm Joe Coughlin. I'll be moderating the event for the next 2 days, working with Abigail Glenn Chase from NARI. We wanted to go over a little bit of the agenda up front and some of the logistics before we get started. Today, we're going for 2 days, from 12 to a little bit after 4 o'clock. We're going to leave some time for questions between about 4:15. Obviously, we just had our opening remarks from the Associate Administrator, Bob Pierce. We're really happy that he took time out of his busy schedule to talk to us and really emphasize the importance of what we've been doing and the importance of transferring our capabilities that we've developed so far out to the community. Our agenda, is we'll go over logistics, and we're going to get an overview of the system-wide safety project, which has been the caretaker for this research, and Misty Davies will be speaking to us. And then we're going to shift into more of the problem space, get a little more technical with Guillaume and Terry. They're going to talk about the capabilities that have been developed, the problem space that they operated in, and the solutions that they provide. And then we're going to have two speaker panels. The first one is going to be from our important stakeholder, the FAA, and they're going to give a perspective, and Natasha Naogi will be moderating this panel. And then another panel, the second one, will be from the research community's perspective with peer organizations like NIST, DARPA, National Transportation Safety Board, Air Force Research Lab. And then do we want to cover day 2? Can we do that real quick? Okay, all right, so now Abigail will take over and describe some of the logistics.
Joe, we can we'll have the agenda up for our closeout today, and we can go over day 2 at that point. I'm also will update this agenda. The title of the of Guillaume's panel is Government Peers Perspective. So looking forward to both of those today. Thank you again, Joe. And hi, everyone. Good morning. Thank you for joining us. You are watching this presentation through a YouTube live stream. There's a unique link each day of the event, which you can find on our event website and in your inbox each morning. A couple notes on using YouTube. If you prefer to use closed captions, select the CC icon on the bottom right of the YouTube menu. And the subtitles can be dragged around your screen in case they are cutting off any important content. If you're experiencing poor video quality, select the gear icon also on the bottom right and adjust the settings from there. We are broadcasting this live, though you can pause at any time. If you do so, but you want to catch up a little later, click on the word live in the bottom left. Please feel free to use the chat in YouTube, which will be monitored by my amazing colleague, Jonathan Nguyen, though we will not be taking questions officially through that platform. Next slide, please. We do value your questions, of course. They're a vital part of this and every NASA NARI event. So we're going to be using the Conferences.io platform through our general session. This is an audience engagement tool called Conferences.io. The link is on this slide, but you can also find it on the event webpage, and we'll also post it to the YouTube chat as well. Nothing to download or anything. You can just go to the site on any device, ask questions, and upvote other questions that you find compelling. If you experience, you can go to the next slide, please, Jonathan. Thanks. If you experience connectivity issues, we have a few troubleshooting tasks that we'll ask you to try before you reach out to us. The most common is slow or poor connection. This is often a hardware and Wi-Fi issue. Try moving closer to your Wi-Fi router or plugging in directly if you have that capability. If you have house or office mates who are streaming content or using telecommunication platforms over Wi-Fi, you can politely ask them to disconnect momentarily to see if that improves your experience. You should also check your video quality settings in YouTube by selecting the gear icon in the menu bar. If you do not have internet connection, restart your modem and computer. If there's a local or regional outage, unfortunately, you'll need to contact your internet service provider directly. If the technical difficulties are on NASA's end, please monitor your email account that you used to register. We'll send information as soon as possible regarding contingency plans and providing alternate access details. Depending on the type of tech challenge and where we are in the agenda, we may decide to switch platforms completely These slides that I just went through are all available under the workshop details on our event webpage, in case you want to reference them throughout the event. And finally, if you need assistance, we are here to help. You can ask for support through the YouTube chat or conferences.io, or you can email arc-cal-nari@mail.nasa.gov. Nice little mouthful right there. If you are a NASA employee, you can also reach me and Jonathan on Microsoft Teams. I'm under Abigail Glenn Chase, and Jonathan is Jonathan M. Nguyen. All right, so thank you so much for lending your time and expertise to this important workshop. Joe, back to you.
Thank you. Welcome to the meeting. I want to go over a little bit of why we're having this meeting and give you some resources. So first of all, the two purposes. One of them is to close out a critical commitment that we made, that we were going to deliver validated methods and recommended practices, and these were going to reduce the cost for certification of both aircraft and ground systems, and doing this through expanding the acceptability of analysis for certification. So in order to meet that, we wanted to communicate the results to maximize public awareness of our research and transfer capabilities via a set of on-demand training seminars and supporting materials, including reports and publications. And so they'll be available as part of this meeting, and they will be available after the meeting. And we encourage people to look at the results and possibly incorporate them in their own research or apply them. Next slide, please. There's some suggested NASA online resources I wanted to bring to your attention as you're attending our meeting. You may have some questions or want to understand a little bit about what's going on. So there are programmatic websites to describe aeronautics research. We have technical links such as the Formal Methods Research Program and Robust Software Engineering groups, where research results and papers are, and other interesting things are there for the science community, research community. There's an important NASA technical documents report server, and a lot of NASA's public-facing materials are put on this server, and they're available. One of the advantages of using it is that typically these reports are available free and not through a for-cost publication venue. So it's a good place to go and look for papers. You'll find papers describing and other artifacts describing what we're talking about through these 2 days at that site. And then finally, I'd like to talk a little bit about open source resources. NASA uses open source to accelerate software development and to get our results out to the community. We have an open source policy that's available. There are repositories that we use, SourceForge and GitHub. These are common repositories that other people in the community use. Our software is available there. And there's also a catalog, and the catalog is at code.nasa.gov. And it lists all the software, not only that we've developed for the aeronautics research program, but across the entire agency. And I encourage people to look at these resources and explore them. Next slide, please. Motivation. So as Bob Pierce said, there's a need to improve the delivery of and the certification of systems, and they're becoming increasingly digital. They're more complex, they're software intensive systems. And as we've moved in this direction, the legacy processes and techniques that we use to do certification have become at times barriers. And so there was a need to do a more fundamental research to improve the ability to apply and deliver methods and reduce the cost, especially of these mission or flight critical systems. And this was identified back in 2006 from the National Academy. And NASA has a role because of our supporting infrastructure, our mission alignment, and the lack of alternative sponsors. Now, what we're talking about in this meeting is predominantly material and results that we've developed over the course of the last several years, but there's research that is ongoing. We're not stopping. And their motivation for that research can be found in the In-Time Aviation Safety Management Report, which is also at the National Academy. So there's this driving need that the National Academy has identified. NASA has a role, and we're fulfilling that role in this software intensive, in this system-wide safety project. Next slide, please. So you'll see a lot of the about this in-time aviation safety management system. This is the long-term goal. It's a system that is going to be more adaptive. It's going to include conventional standards, software intensive systems, and novel systems. What we're going to be addressing in our meeting is more the current applied and existing systems using modern methods on traditional. There's another element that we'll talk about on the second day, and it has to do with bringing in what people would call AI or adaptive machine learning. And that is, while not covered in the technologies that we're going to talk about, we'll have a session on that coming up tomorrow. Next slide, please. So here's a list of on-demand training seminars. There's 10 of them that we've developed for this meeting. They're going to be available at the website through a set of links. Just wanted to go over them a bit. They're listed primarily in alphabetical order here. Most of these are tools, but we also have a process training seminar on how to approach the problem. We also have a case study using the compact positional reporting algorithm and Precisa. So there are videos available. They run from 30 minutes to a couple of them have a couple hours long, broken up in sections. Beyond just the on-demand training seminars, next slide, please. We also have additional capabilities. These don't have seminars, but they're tools that are available. Some of them are in development. They're not completed, but we wanted to bring them to your attention because it's part of our research portfolio that we still have ongoing. And they're also NASA contributed capabilities that through funding and collaborating with industry, we've developed, and those are also linked in our website for the meeting and available for people to look at and explore. Next slide, please. So we're kind of organizing our technologies instead of alphabetical order like the previous slide. We decided to kind of organize them across the development process, the design cycle, from requirements gathering to maintaining and distributing and deploying systems. And so this slide kind of lays out where the technologies sit in the tools and processes sit in the development cycle. And they are also linked to a set of landing pages for each of the technologies and processes. I'd like to click around if I can to some of these capabilities, and we're going to do this. Here's our website. And I'd like to start with overarching properties, which is it's really a process. It's a way of approaching a problem. Michael Holloway is the lead for this. Michael's produced 3 training seminars, and there also are a set of papers. We call them capability links, but they're basically publications and technical reports describing the process that one would follow to improve the quality of certification. Then next, I'd like to point to the FRET tool. This is a tool about gathering requirements and structuring requirements in a way that they're correct and they can be analyzed and tested. So this is a technique that allows us to explore requirements and make sure that they're achievable, rather than having poorly written requirements cause a set of cascading problems later in the development process. There's a link to learn more about FRET. There's a download link, and there's also the training seminar. Thank you. So go back to the diagram, and now let's look at Precisa and CPR. This is an interesting element because it's really a use case. There's 2 complementary talks, both by Aaron and his team. The first one describes the framework that does a floating point analysis, and it's available as a download. And then secondly is the, we go back, CPR, which is a position reporting algorithm. This is an analyzed, and there's an encoding video, and then there's a application video right below this one. So just right below, yeah. So the application of it to identify locational calculations and make sure that they're precise and that aircraft are identified in the airspace correctly. All right, can we go back? All right. Then on the, there's another technology called AdaStress, which is more on the testing side of the house. So getting away from requirements analysis and algorithm analysis to doing stress testing. So AdaStress is about testing a system that has been developed and making sure that it meets requirements. There's a learn about, and then there's a download for AdaStress. Can we go to the download link, please? This should be available on GitHub. Yeah, so software is available along with documentation. Thank you. Okay, can we go back to the V chart? Yeah. So this is explorable. It's linked to on our main web page. And then below the V, there are additional capabilities. Some of these are, well, these have been involved at NASA and external entities we funded. They go from case studies of DO 330, 333 to participating in a larger community. All right, and so please explore these links, look at the content at them. There are landing pages for each of the technologies. And with this, I think I've covered. Can we go back to the slide deck, please? All right, so now we're going to transition to the system-wide safety project overview. Misty Davies is the System-Wide Safety Project Manager. She's been involved with the project for many years, took over as a project manager about 18 months ago. I've worked with Misty over the years, really enjoy working with her, and she's an excellent speaker. I think we're going to really enjoy her presentation. Thank you.
Thank you, Joe. My name is Dr. Misty Davies. I am honored to be the project manager for the System-Wide Safety Project. System-wide safety is in the Airspace Operations and Program Safety Program within the Aeronautics Research Mission Directorate at NASA. System-wide safety began in 2017, and we inherited the work that you will see us talk about today and tomorrow. This work is foundational to the core of System-Wide Safety's mission, and I'm really happy to talk to you about that mission and a little bit about how this work fits in today. Next slide, please. So this slide is a cartoon of the sort of processes and regulations we have in place for maintaining safety in the airspace today. And one of the things that particularly amuses me about this cartoon is that when I show it to people, people who are very familiar with these processes will tell me that it is in fact a cartoon, that it's ridiculously oversimplified. And people who are not familiar with the way we think about safety in the airspace today will tell me that this picture is far too complex and that they can't wrap their heads around it. And frankly, that's because the processes by which we assure safety today are very complex. We evolved here based on many, many decades worth of knowledge that we've gained about how airspace systems fail. The important thing to note for the purposes of our conversation is that if you look at this cartoon, you'll see that there's a line drawn. And on one side of the line are a set of processes and procedures that we use to assure things during design. And on the right is some ideas, some processes, procedures for how we assure things during operations. And those things are fairly well separated. Next slide, please. In fact, even the language we use is different. We talk about certifying systems. That would be machinery, hardware, software, again, within the context of the mission, within the context of the environment. So it's not like we completely divorce them, but we still talk about certifying them. If you look at the left today, these systems are really designed to be deterministic. To the extent that we can, we want to know everything everything about them. We want to be able to walk all the paths. We want to be able to understand every part of the state for the things that we put on the left side. After design, we throw everything that we can't really nail down, that we still have, that we need adaptation for, over to the other side of the wall. In fact, sometimes with my colleagues and with others, I've heard, we'll fix it in ops. So then if you look at the right side of the picture for operations, we don't talk about certifying as much as we talk about licensing. We talk about trust and putting skill and experience in people, the operators for the system, that will follow procedures and regulations. But what we do there is we train them, we test them. And this is the space that safety management systems live in. And in this space, we talk about moving from real-time monitoring to in-time monitoring for safety issues and hazards. Next slide, please. So all of these fantastic procedures have resulted in, frankly, what is an incredibly safe national airspace system, affectionately NAS for short. As the public, we've come to expect that level of safety. In fact, when we have introductions, innovations move into the airspace system, there's almost unavoidably some unknown unknowns that pop up. We have a transient change in the safety profile. And when that happens, it's newsworthy. We follow it. We talk about it as a society about those changes. Because we have that low tolerance for risk in aviation, that's made it really, really hard for the new entrants, for the folks who would like to bring new concepts in aviation. That's made it hard for them to enter into the market and to really introduce these novel ideas. And frankly, the cost is so labor intensive for our current level of safety is that even our traditional aerospace companies have a hard time introducing novel concepts. There have been fantastic innovations, even Delta innovations, that large companies have told us that they haven't brought it to market because just the cost of assuring it, even though they're fairly confident in its performance, would be too high. So one of the things that my project, the System-Wide Safety Project, has been asked to do is to define a concept of operations for a scalable in time. And by in time, we mean that we discover and mitigate these hazards and risks in time to prevent bad outcomes. And in time aviation safety management system. So modifying the safety management system we have today. Because that's the way that we're marching, and I'll talk a little bit more about it in some future slides, we're envisioning a service-oriented architecture. And that we believe will let us better focus our safety investments and overcome these barriers, let the emerging entrants and the novel innovative concepts be brought to the market, enrich all of our lives. So in general, because this is an outreach event, I would like to praise and say thank you to our stakeholders, both industry and regulatory, and our academic partners. First of all, for walking with us, for collaborating with us, and also as we sort of look to the future, how do we build on this work? Since this work is foundational to what we do, help us learn about what the consensus is for the new desirable system traits. Give us relevant use cases. Walk with us, help us understand how to integrate the data and leverage these new automated autonomous systems as we march forward. Next slide. So this is the space of the national airspace today. These are all the different domains that in one way or another we're working. It certainly consists of commercial, traditional aviation transport as we know it today, as well as general aviation. But honestly, NASA already has work looking at high altitude operations, the new ones that are emerging, plus space launch operations. We're already increasing not only traditional regional transport, but emerging regional concepts. Recreational UAS are taking off. We're increasing the use of large UAS for our benefit today. And then, the big, heavy, push at the moment is these novel concepts around urban air mobility and increasing use of low altitude unmanned aerial systems in order to better our lives. Next slide, please. If we look today at how the system operates, I'm going to say this a little tongue in cheek, but if you think about where we want to go, this is a comparatively centralized system. We've evolved to this over time, so there are really very formalized roles and responsibilities of everybody operating in this system. And part of how we manage this is this really incredibly well separated airspace. Next slide. So talking about the evolution. So if you look at sort of the introduction of aviation, really we were focused on safety almost immediately upon using aviation for especially passenger transport early on. Safety became the focus, and that led us to put many, many procedures in place. Frankly, our big concern was, our ability to actually just know where the vehicles were. And so, the big innovation early on was really just being able to estimate the current and planned aircraft positions. As we added more and more vehicles into the airspace and we added density to the picture, the big innovation there was radar, actually getting to know the current and estimated planned aircraft positions. That's led to where we are today. And so today we start to think about trajectories. So as we manage airspace operations and safety, a lot of what we're doing is focusing on the known and exchanged current and planned aircraft positions. We've started to automate some in-time safety monitoring and alerting services, but really the focus today is on efficiency and on proactive planning. As we think about how we're going to move into the future, we're already starting to see a world in which the proposals are more collaborative and connected. We're really starting to talk about performance requirements, and can we get performance-based metrics into the system to really enable some of that innovation and to keep us safe. And really, there's a bigger and bigger push to sort of having a more collaborative air traffic management system in which we've introduced third-party service providers. This is leading to a service-oriented architecture for these tailored missions and services. And it's really leading us to try to innovate in the areas of integrated predictive risk and to make sure that we're mitigating across domains. And the goal, and really in order to enable this heterogeneity, this diversity and density of operations, is to move to a really highly automated system to enable that future. That probably is going to be machine learning based, based on what we know about now, based on our techniques that are possible. Certainly going to be dynamic. And really, given the scale of operations we're talking about, we're going to have to be thinking about robust performance and safety, where we have much tighter collaboration between the humans in the system and the machines that are making decisions. This is going to increase the complexity. Unfortunately, there's just almost no way to avoid it at that scale of density and at that different kinds of operations in the system. And so, and at the robust performance and safety that we expect that people will still want to continue as we move forward. And so we're really going to have to think about automatically ensuring these adaptive systems still in time in order to maintain safety, to handle threats and manage them as they come up. Next slide. So in the future, as we add all of these new operations, these new collaborative, and again, dynamic, increasing density systems, what I think we're going to see is that we have to have a federated system that mixes the system that we have today and the incredibly safe evolution of the system that we have today, and lives in a peaceful harmony with these collaborative systems in the future. Next slide. And this sort of gives you that the idea of, as we sort of move towards that federated system, how do we handle the safety risks and the different time scales at which we've thought about mitigating those risks between the different systems? How do we continue to manage airspace, and in particular handle contingencies as concerns happen, as failures happen? How do we safely manage those? Next slide. So NASA has proposed, and we'll talk about this a little bit more based on a National Academies challenge, to build out an in-time aviation safety management system. And if you look at this picture today, this is sort of again a cartoon showing just, you know, a really bad day in the life of a future vehicle, where this vehicle wants to take off in one city and land at an airport in a neighboring city. But what happens almost immediately after takeoff is that the passenger has an emergency. And instead of flying the original route to the regional or maybe even international airport in the neighboring city, instead the passenger really needs to go to the hospital. And so if you think about the complexities that have to be managed again in this dense and diverse airspace, it can include everything from non-cooperative aircraft, it can be obstacles, could be weather, could be RF interference, could be GPS degradation, could be any sorts of terrain collision. Could be that, you know, sometimes, you know, when you're having a bad day, it just gets worse and worse. Maybe in addition to the passenger emergency, there's a secondary vehicle system failure, and now we have to reroute other traffic in order to manage a second time constraint. So this is the system that we were asked to envision in the future. What is the system that lets us handle all of these potential hazards in time? Next slide. So this vision came out of actually a National Academies review of NASA's work in 2018. NASA had proposed in time, actually at the time we said real-time system-wide safety assurance. It was actually the National Academies who corrected us and said that not everything needed to be real-time, that it could in fact be in time, that's what mattered. And they're the ones that challenge us to move from our original vision of thinking about each of those hazards separately to thinking about them as the system as a whole, the full safety management system. In particular, they identified 4 fundamental system element development areas that they thought NASA should handle. The first was the concept of operations and risk prioritization. This in itself is a bit of an elephant to eat. If you remember that earlier slide where I showed you all of the different domains, everything from space launch to small UAS to emerging air taxi vehicles, each one of those domains has its own set of risks and hazards and prioritizations. Even within UAM, if you talk to current day UAM companies, their concepts of operations can be so widely varying that their functional hazards and risk assessments look very different. And then our challenge is to come up with system monitoring, system analytics, and mitigation and implementation for all of those risks and hazards. Next slide. So today, this image comes from what's called the Safety Management System Bible, or ICAO's Annex 19. There are 4 pillars of the safety management system. They're safety policy, risk management, safety assurance, and safety promotion. And under risk management and safety assurance in particular, this can be broken down even to further subcategories. Under risk management, we've pulled out hazard identification, risk management controls, and safety performance. And under safety assurance, we pulled out data collection, data analysis, and resource prioritization. If you think about how this system has to change in order to achieve that IASMS vision, next slide, please. Sorry, there was an extra little bit in here. There we go. If you think about how this system has to change, what you see is that those risk management and safety assurance pillars have to merge. That is the in-time system-wide safety assurance vision that we originally promoted to the National Academies, and that the National Academies challenged us to broaden. We've broken this down a little further. We now talk about different services, functions, and capabilities that are parts of that in-time aviation safety management system. Instead of just thinking about hazard identification or data collection, we now talk about the monitoring parts of the system, because what we see is that there's much less difference now, again, in that pillar between the safety assurance and risk management parts of the pillars. Similarly, risk management controls and data analysis have become a single assess function. And then safety performance and resource prioritization have become part of this mitigate pillar. One more slide, please. So now we have this merging. Oh, sorry, one back. So now we have this merging where we now talk about managing the known operational risks, identifying the unknown risks, and then feeding that back, informing the system improved through system designs. Next slide. All right, so back to where we started. So I'm going to spend a little bit of time here. As we look at how the system overall has evolved, the reason I've spent all this time talking about the operational system is that it greatly affects now what we do in design. If we're going to move towards this much more rapidly evolving operational system, we can't be as labor intensive on the design side as we are today. But we still need to be able to maintain or even improve our current levels of safety. That's what society expects from us. Assurance requirements today are really specific to flight rules, to the operational complexity of the system, and risk criticality. Services, functions, and capabilities have to be assured to that appropriate level via an acceptable process. So all of these things that I've been talking about on the operational side still have to be handled at the design time. One more slide, please. And so this is sort of the most important point. As we move forward towards increasingly autonomous systems, we think there is going to be very little difference anymore. There's not going to be this wall that divides design and operations. We're going to have design parameters as we design things that are expected to adapt to the operational considerations and constraints. And we're going to have to start designing to manage unknown unknowns. That's going to feed forward into operations, where as we learn these new operational considerations and these new constraints, that's going to now have to feed back to design again. And we're going to have this continuous loop in the system. So let me really quickly move over to conferences.io. I'd like to I'd like to answer some of the questions in questions.io. So one of the question is one of the comments in the chat is that no one's ever presented a credible argument showing that assurance costs are too high. I think there are actually pretty impressive documentation showing that as much as 70% of the costs of some systems are currently to assure safety on systems. Now, that's probably 70% in itself. I would probably agree with you, isn't too high. But when we have new entrants who tell us that they can't achieve systems, and when we have our current industry partners telling us that they're pulling capabilities off of systems that in the end might have improved safety, but they can't show that it does, that does become a challenge. And that's part of the reason why NASA agreed to do it. Let's see, I'm handling the questions I think I can speak to. We'll get to all the rest of them. NASA is, we do support quite a few different approaches. We do have collaborations with folks who are advancing STAMP and STPA. That is in our portfolio. And let's see, it looks like moderator's already answered a question about how this is coordinating. How much support does this V&V research effort have from the divisions of NASA dedicated to commercial space standards? We collaborate with the space side of NASA. So, and I think there'll be some discussions about that, I think, further on in the workshop. But that is work that we do. So there's a comment here. Some of these are, I like it. I think our audience has strong opinions. ARP 4754A and ARP 4761 are decades-old reliability methodologies that focus on component reliability and fail to sufficiently address increasing behavioral complexity. What is NASA doing to investigate new hazard analysis and control techniques that move beyond the limitations of these old standards? Well, I'm hoping that you'll hear a little bit about what we've been doing over today and tomorrow. And there's certainly work in our portfolio that we are not closing out that is continuing that work. We have been working with the standards committees to update those standards in particular, and we'll continue to march forward. The slides should be available. Usually all of these slides are posted at the same NARI link. And I imagine that Abigail will probably show that to you several times today. All right. Okay. Unfortunately, I can't answer the overarching properties questions directly, so I'll have to handle, but we'll try to get one of the team that's working on the overarching properties questions to answer those specific questions for you. Hi, Joe. Thanks.
Hi.
All right. I believe all of the links will be posted within that PDF under the slides. So we will be able, that will be on the website. And my guess is that if you were receiving an email, if you registered for this through the NARI link, that you should have the original link that you registered at, which is where these materials will be collected and linked from. Plus, Abigail will probably send out another link as we move forward in those emails. So again, I'm a little sad that we're running fast this morning because I know that the panels almost always run slow. We get into such great conversations.
Yeah, Misty, the main webpage has a link now to the V&V chart, the development V, and those links in that chart go to the capabilities that I showed earlier, so people can get to that just from the main webpage right now.
Can we put the link to that website back up on the screen, maybe just in a blank piece of paper or a document? It's not as easy as putting a link up on the YouTube channel. Yeah, that might be possible too.
Sure, give me one sec.
All right, I'm still monitoring conferences.io if anybody has any last minute questions they want to put in here.
Also, the most of the capabilities that we have in that chart are available at code.nasa.gov if they're released, because that's a repository for all our software. And then that NASA Technical Report Server, a search there on any of the names would come up with the key papers, and those should be accessible without a paywall in most, if not all, cases. So,
thank you, Joe.
You're
perfect.
welcome.
All right, give me one sec. I'll put this up right now.
So we're going to continue to be responsive to anything that's put in the conferences IO chat. So again, please put that there. we are seeing the overarching properties questions. I will tell you right now that I greatly respect those researchers and I don't want to say anything wrong. So I'm going to let them respond to that directly. And we'll drop a line to that to them and get the answers for you.
All right, well, thank you so much, Misty and Joe. Guillaume, if you're ready, we can just jump right into our next session here.
Well, I'm still here. Ready is another question, but okay. And maybe I'll start with actually a little reminder. So this is a closeout workshop for TC3, right? Lots of the questions I'm seeing on Conference IO are related to TC3, but they're almost more related to what we're doing now in TC4 and TC5. So you might be a little bit disappointed in the answers we provide today, because this is basically presenting work that we've transitioned, and since then we've transitioned to address new challenges. So don't expect to see answers to everything you're posting in the chat today. And I would point out that next we have started an effort in TC4 to identify more gaps and needs in VNV and assurance for aviation systems, and this time we're targeting more the upcoming aviation systems. It is something called VNV Vision VNV 2045. And next week on July 19th through NARI, we will have a workshop that will inform you about where the team, we posted an NRA last year on this and selected a team to realize that study. And they'll show their current, I would say, current state of the affair that they have, and we'll welcome any inputs for this type of systems next week. So maybe later on, Abigail, we can post, or maybe on the website, we can post a link to that workshop next week, which is on July 19th. Okay. And so that's to address those comments. And if you want to put back the slides, I can start on the slides on TC3. Okay. This I will present it, and we'll be presenting the history of what we've been doing. But this is work that's done in a collaboration fashion between Langley and Ames. I'm more on the Ames side. Terry is on the Langley side, and I would to start with acknowledging the people that were there before Terry that did an incredible amount of work, leading TC3, and that's namely Paul Miner and Eric Cooper at Langley. Paul is still on the project as a project scientist, as an advisor, and Eric has moved on to line management, but they've done an incredible amount of work in the first 10, 12 years of this project. Okay, next slide. So there was a question about the space side of NASA. This project was really funded by ARMD. Okay, it's done in the System-Wide Safety Project, which is part of the program, the AOSP program in ARMD. And since the funding was coming mostly from ARMD, we really focused on aviation. That doesn't mean that the techniques and tools we've developed are not applicable on the space side. And we're certainly now trying to push them into missions that are more on the space side, especially the small sat missions. And over the years, we have been in touch with the people working on standards at NASA on the space side, especially the Office of Chief Engineers. And they've used some of the tools and asked us to do studies with some of the tools, like the static analysis tools that we'll talk about. Next slide. All right, so there was a question about the cost of VNV in the chat and saying that it's controversial. We started this not with a specific goal in mind, but we really started this by talking to industry. And really the message we got from industry at the time, and we're talking 2009, 2010, when we started this VNV research effort, the message was the cost of VNV is really too high, and the cost of VNV for certification is really too high for industry. And they were asking what we could do to help with this. So one of our first thing was to try to figure out where that cost was coming from, and that really shaped the strategy that we used in this research program. Since then, we've been talking even more with industry, and especially the new entrants, meaning those new companies that were not part of traditional aviation, but that came up, who started showing up, trying to address the need for autonomous systems. So that has been shaping how we evolved from TC3 to TC4, the research that we've been focusing on. But really, this talk is about the message that we had at the time and how what we could do to address it. Okay, next slide. So really, there's been studies that looked at where errors are showing up when you're developing software for complex systems, especially in the civil aviation space and defense industry. And it was noted that really the cost of detecting, and I'm emphasizing detecting and fixing an error, goes up exponentially as you caught the error later and later in the life cycle. There's almost like a factor of 10 every time on there, like a jump in the magnitude from one phase of development to the next. So really, when you look at this, the simple lesson was, why can't we do VNV earlier in the life cycle? And that's really what has been really driving us in this in TC3. Next slide. So to really hammer the point, there were studies that showed that up to 90% of the problems were introduced in the phases from requirement to development, software development. And then actually most of the VNV techniques being used relying on testing. So 96%, over 96% of the faults were found actually late in the process, which means that if you're finding it late, maybe you can correct it quickly, but some of those might actually lead to redesign and to go over the loop, the development loop, and the V diagrams, and that basically drive the cost up. Okay, so really all of this pushed us to look at techniques in software assurance that could be applied earlier in the development process. Next slide, please. Right, so Joe has shown that V diagram. And really what I explained so far is the reliance on testing and means that we're catching errors very late. And what we're trying to do in TC3 is develop tools and techniques that can catch the problems much closer to where the problem has been introduced. So if it was a requirement problem, then we would like to try to catch it at the requirement level, or maybe in design, but certainly not once we've implemented the whole system. Okay. Next slide, please. So when you're talking about applying V&V techniques earlier in the process, testing becomes really hard to use because you don't necessarily have something that you can execute or simulate. So we turn to formal methods and try to really use those earlier in the process. And that means that you have to formalize a lot more what's being done in the requirement phase, the design phase, even in the coding phase. So it's really going to reduce the reliance on testing, but our goal was never to eliminate testing. It should always be there. And I would say that our goal was to push assurance earlier in the in the development process so that we can fly through testing. The goal is almost as let's not catch anything in testing. Let's fly through testing. That doesn't mean that we reduce the amount of testing or the efficiency of testing, but we really don't want to catch errors there because that means we did a good job earlier in the process. Okay. So the other aspect we wanted to address is the complexity aspect. The systems are the reliance on software is getting bigger and bigger, and the systems are getting more and more complex, and more capabilities are introduced through software. So the job of verifying software, assuring software is becoming harder and harder. So one of the things that we've been investigating is the use of compositional V&V techniques to address that scalability challenge. Now, if we bring in new techniques, new assurance techniques to bear, then we have to make sure that the certification process that's recommended by the FAA accommodate those techniques. And we had researchers working on evolution of the DO 178 standards to ensure that those techniques can be taken advantage of during certification. Okay. Next slide, please. So we've developed really a lot of tools and techniques as we work through this research program. I'm going to try to describe some of them, and I'll do a very cursory presentation of them because there is no time to dive deep into every one of them. But I encourage you to follow the links that Joe talked about and to look at the tutorials we have on some of those. Okay. And then I'll try to point out for each of those techniques if things related to the impact that they might have had, and especially have then been used in industry outside of NASA. Okay. And that's to show that TC3 was not just a theoretical exercise, but we really tried hard to have an impact on what is done in industry. Okay, next slide, please. All right, so Joe presented that V diagram, and we tried to put some of those techniques on that V diagram. And you see that there's quite a few that are on the left side, and that's to follow our strategy to address, to push assurance and V&V earlier in the development process. You still see some on the right that talks about improving testing and how can we find more corner cases instead of relying on the traditional testing techniques. And then we didn't forget that some errors might make it to the field. And we worked on runtime monitoring techniques so that we can catch those during operation. Okay. I'd like to point out that's not only runtime monitoring. Those techniques can also be used on the right side of the V as runtime analysis techniques, meaning that when you're running your test cases, you can actually have smarter test monitors through the use of those techniques. And everything we're doing in VNV would have been, or everything we've done in VNV would have been useless if we didn't have also, if we hadn't looked also at the certification process. So there are lots of questions about overarching property. And like Misty said, I'll let the researchers working on this provide better answers. But keep in mind that one of the starting points of the work on overarching properties was to look at DO 178 and really boil the essence of DO 178 into those three properties, overarching properties, and to try to free people from having to stick to the burdensome process described in DO 178, while still keeping trying to address the essence of DO 178. Okay. There have been also questions about safety case, and we have done research to support the use of safety cases for certification, which is always an alternative method that people can use to do certification. Is just actually a little bit harder to do, since you're not just checking boxes in a standard, but you really have to show that you've retired and mitigated all the risks. And that's the work with Advocate. So I'll try to cover most of those works, and I'll pretty much follow a left side of the V going back to the right side and finish with techniques that address a little bit more certification. Can we go to the next slide, please? All right, so one of the techniques that we have been using very early on that's applicable almost at the operational concept level, or when you're looking at algorithm, is actually the use of theorem proving. And that's a pretty heavy technique to use, but it can be extremely useful in finding problems with the algorithms that are going to be implemented later on in the development process. So we have done substantial contributions to the PVS system, which is one of the most known and used theorem prover out there. And you see some of them are being listed here. And I would point out the very concrete and useful one in the use use or the improvement in interval arithmetic and fine arithmetic. Those are techniques that allows us to apply formal methods down the line and that have application beyond just in theorem proving. And work on exact arithmetic, for example, has been instrumental in developing static analysis technique that can look at the use of floating point computation in code and how you can prove them being correct. So all of those can have been made available publicly, and we try to do that with most of our work, and sometimes it's on GitHub, sometimes in other places, but we're working hard at making our research results available open source. Okay, next slide, please. So one of the application of in PVS is PVS IO checker, which is basically targeting validation through model animation. And I gotta come clean. We focused a lot on verification and not so hard on validation. So that's one of the work that's actually addressing this. And the goal was to formally verify some algorithm using PVS. And the focus, like I talked about in the previous slide, was especially on the use of floating point computations. Okay, and that has been released as part of the PVS library. Next slide, please. So the next step was to look at really what could we do in requirements. And in one of the panels today, we will have somebody from NTSB, and some of the discussions we had with NTSB. And I'll remind people that it's NTSB, a big part of what NTSB is doing is investigating accidents or incidents in aviation, not only in aviation, but also in aviation. And the point, when we talk to them, they point in the fact that a lot of the accidents they've seen are due to problems in requirements. So one of our focus was, what can we do at the requirement level? Okay. And to do anything about requirements, really any type of assurance, since we cannot do testing, is really to formalize requirements so that we can do some formal analysis of them early on. Okay. They still haven't been refined in a detailed design or in code, so they're still in some sense vague enough that you could if you do an analysis on it, you might have problems showing up that won't be showing up later when you refine it, but it at least focuses your attention on some of the possible problems that can be coming. Also, since down the line we want to use formal methods and to analyze design models or code, then we want to relate those analyses to requirements. And for that, we need the ability to formalize requirements. So we have safety or assurance targets for analysis down the line. So the big problem was, okay, we could turn to some of the languages that have been developed over the years to create formal requirements, and there have been many. But the truth is, none of those were really adopted in industry. And the standard was still writing English-like or requirements in plain English. So what we wanted to do with Spread is try to give a capability that allows you to write your requirement as close to English as possible, but kind of guide you while you're doing it so that you can really, it's easier to formalize them behind the scenes. And that's what you're seeing in this slide. So you can see a text editor on the left that guides you. Really, there's a grammar behind the text editor that guides you to writing your requirements so that it's easily formalizable in the end, okay? And for that, we decompose requirements in several sections that are talking about the scope of the requirements, the conditions are being described, the component for which it holds, the timing aspect, and very often, at least low-level requirements have some types of response to conditions that may occur. So that allows you to organize your requirements and write it so that we can actually formalize them using some kind of temporal logic. Okay. Now, validating that you've written that your formal requirement is really what you wanted to write is hard, because if you were an expert in writing formal requirements in the first place, you probably would be would have an easy time validating that what you've formalized is what you wanted to express. But for the common engineer, that's not easy. So we've created like a visualization, a sort of a visual simulator that allows you to picture what your formalized requirement is actually expressing. And we've been working with some people in industry, and we're seeing a lot of interest in Fret. Truthfully, the research is not done. Then there is a need for more capabilities. And we will be working those under TC4 and TC5. Next slide, please. So now we have a capability to formalize requirements. How can we use those formal requirements and really verify them against models in design? Again, there's a lot of languages that can be used in design for doing modeling. SysML and UML being very popular. Unfortunately, they lack a little bit of formalism. So we looked at what are the other languages that are being used a lot for control system in aviations, and Simulink was one of those. Okay, and truthfully, it was hard to tease out the semantics of Simulink. They're not published openly, so we had to derive them from experiments. But we managed to actually tease out those that formalism and generate or use techniques that are used in model checking to verify formal requirements on Simulink models. The nice part about this is that we fully integrated the work that was done under this tool called CocoSim in the Simulink environment, and you can really click on a menu in Simulink to start CocoSim and actually generate do your formal analysis of the model. So I said that it relies on model checking. So basically, in essence, what it does is it takes a formal requirements and turns it into a monitor that we couple with the models, then the model that we want to analyze. And when you trigger an analysis, it's going to tell you, yes, that formal requirement is met by the model, or it is not. And if it's not, then I'll give you a counter example that you can replay in the simulation environment in Simulink to try to find out what the problem is. Again, that's a work that's available open source. Next slide, please. All right. Another work in formal verification is the Kodiak library that has been done at Langley. And this is really work that's linked to more like a theorem proving, but that can be used to formally analyze a C and C++ code. Okay, and the target was again to try to use we targeted a branch and bound algorithm that's used a lot in this type of work. So it's you can think of it as a way of bounding what you present in code, bounding what the functions that are represented in your code with a nonlinear inequalities that represent a safe abstraction of what the code is implemented and allows you to really reason about what's being done in the program. And you'll see more work along these lines at the code level. Next slide, please. ICOS is one of those also that's using a sort of a mathematical representation of what the code is doing. So again, we represent what the instructions are doing in the code with safe and conservative mathematical representations that can be analyzed, and that allows us to point out errors in the code. There are actually commercial tools that are available in static analysis, but what we didn't like in them is that they were either scaling well to large code base, but were very imprecise and were generating tons of warnings. And when you generate tons of warnings, the tendency is to completely ignore the results of static analysis. And the opposite was work that was trying to be much more precise and generate a lot less warnings, but those were not scaling to large code base. So we set up to develop ICOs with the goal of analyzing at least 500,000 lines of code in a precise fashion. And we did this by basically biasing the algorithms towards what's being used in control systems. Okay. And that's another work that's available on GitHub. The link is not on the slide, but you can find it in the material that Joe provided. Okay. Next slide, please. So this is another work that does static analysis, but it's focused on a narrower set of problems. The focus here was to really focus on floating point arithmetic, or the use of floating point arithmetic in code. As you are using floating point representation in your code, and you're doing more and more computations, error in floating point representations can accumulate, and you might end up with results that are completely incoherent. A good example of that was the application that we did of this work on the CPR algorithm and the CPR code that was described in the standard for CPR. And it shows that basically you could end up with an error that was such that you could be 300 miles, you could have an error of 300 miles from in the representation of what CPR was giving you. CPR being a way of locating where you are when you're flying. So that can have large impacts in aviation. So the results of this floating point analysis has been integrated in a tool that has been developed in Europe that's called Pharmacy. That's another research static analyzer, but that's available openly. Okay. Next slide, please. So what we've been talking so far were techniques techniques that can be applied on the left side of the V. We saw Fred that was addressing requirements, and then we saw Kokosim addressing design models, and then Precisa, ICOs, and other work that we've done on basically the Bernstein library to focus really on the code side of things. Now we're going up the right side of the V. Like I said, it's what was favored in industry. Most of the V&V was done using testing. And we thought that this side could also be improved in the sense that even if you were doing testing and providing a coverage that gives you close to 100% MCDC coverage, for example, you would be missing problems with testing. So we started investigating techniques that could be a little bit more focused on trying to find corner cases. So that's what's called usually stress testing. And that's what we're trying to do with data stress. Our first target with data stress was something that was kind of in between traditional aviation system and the systems that will be used for autonomy these days. So the focus was at the beginning on the ACAS-X standards that are being deployed and the prototypes that are developed as part of the standards for ACAS-X. ACAS-X being the next generation of TCAS, the collision avoidance system being used on planes right now. So in ADAS-TRESS, what we did is to take advantage of AI to try to really drive the testing towards interesting test cases. So think of it as as in this case, a reinforcement learning feedback loop between the output of your test and the inputs you're feeding in terms of test cases. So that feedback loop looks at the output and tries to drive or generate new input cases so that you can drive the testing towards more interesting test cases. And when you use a reinforcement learning framework like in ADAS-TRESS, then you can indicate what you care about in the cost function for your reinforcement learning. So that was very successful in terms of ACAS-X, and we found many test cases, many error cases that were interesting to the ACAS-X development team. And then we went on to use this technique with other systems. And one of our collaboration with GE was actually using ADAS-TRESS with their flight management system. And they were so pleased with the results that they decided to fold ADAS-TRESS in the continuous testing framework. So that's an example of the impact on industry for our work. So next slide, please. All right. So this is another example of an advanced testing technique where we're trying to refine the inputs of during testing based on the results that we see on the outputs. So it's again a feedback loop, but it's not done already learning, using learning, but it's not using reinforcement learning. It's using more like traditional statistical techniques. And the goal there was not so much to drive to corner cases, but to try to actually characterize different risk classes. So this is something where we used actually a space application to drive this work early on, which was a Padabort, which was a code to abort the, I think that was the next generation shuttle at the time, to abort it right on the, when it's on the pad, when you're about to launch, before it's being launched, basically. So we did apply it to the code for Padabort, and we really wanted to represent all the risk classes. That's what you're seeing in the diagram on the right. And later on, we generalized this technique, and one of the uses that we're seeing for it is when you have test inputs that are leading you to interesting test outputs, and those could be interesting in the sense, well, my system is performing well, or that could be my system is not performing well, is to try to generalize and identify a region that behave the same as what you're seeing in your interesting output. So let's take the case of an output being really what we want. We use the statistical learning to refine the inputs and try to find all the inputs that can drive to the same type of good behavior. And in some sense, that would give you a safe operational region for your system, for example. And if you stick to that operational region, then you know that you're going to be safe in terms of the use of your system. So SWS was looking for corner cases. Margins was more calling for or looking for a generalization of the risk in classes. Can you go back one slide, because I think you jumped over slide. Okay, so next slide. Okay, now we're going into techniques that can be used at runtime when your system is actually fielded. Bear in mind, like I said earlier, that those techniques can also be used during testing if you have simulation capabilities. And the nice thing about them is that they actually try to monitor the execution of a system or the simulation of a system and try to relate those to what you've been stating in terms of safety during your requirements. So, for example, if you had formal requirements that you've been generating, for example, using FRET, then you could use runtime monitoring techniques to monitor those formal requirements during operation. And that's what some of the tools I will be describing now are trying to do. So RTE2 is one example of this. This is one where we're targeting onboard runtime monitoring, essentially. So it's, for example, integrated with framework or execution framework that are being used like in space or in robotics applications, so namely CFS, CFE, the core flight software on the space side, and ROS, the robotic operating system, for example. So those RTE2 have been integrating with those so that it can do monitoring on those systems. So it's not just space applications, since they've been used in UAVs in some projects at NASA. But essentially, what RTE2 is doing is monitoring formal properties. It can go beyond that and, for example, do some prognostic, like Bob Pierce was talking about during his introductory remarks. Okay, next slide, please. Copilot is another one of those work, and what's interesting with Copilot is that we really try to take a formal approach from start to finish, meaning that your runtime monitoring system is developed using a formal approach that provides you some guarantees about its behavior when you're using it in operation. For example, not only the code used by Copilot has been formally verified, but also the properties that are being used by Copilot are coming from tools that can formalize requirements. In this case, I'm showing FRET, but it can also work with other tools that have been developed under NASA funding by research labs in industry. Okay, and Copilot is one of those that is being used in other technical challenge in SWS for flight testing, for example. Next slide, please. So we talked about with Copilot and RTE2, we were targeting airborne systems. But as we said earlier, we wanted also to address what's done at the air traffic system level. So for that, we developed a framework called RACE that can be used to monitor data streams that are being generated for when you're doing air traffic control. So think of, for example, the data available through SWIM, the SWIM system. So RACE is a system that can monitor several data streams and perform some cleanup on the data that is being generated in by those systems, and in some cases can, for example, reorder the messages so you have a proper causality when you try to analyze what's happening, what's being shown by those data streams is happening live in operation. Okay. So next slide, please. RACE is not doing so much like runtime monitoring per se. We built a system called MESA that does this. And that's a system that really we've put together to do runtime monitoring on those air traffic ATC data streams. And that's work that's jointly with what's done in TC1, where we're trying to, in TC1, we're using data mining techniques to analyze historical data of what's happening during flights and being able to predict ahead of time or identify patterns that are that can be used to identify possible problems that could occur, but haven't occurred yet. Okay, so what we did in that conjoint work with TC1 is that we took some of those patterns that they've identified and turned them into formal properties that we can monitor using MESA and RACE. And that's what you're seeing at the bottom of the slide. And that's work that had been done on the AirNav star protocol that's being used at upon at the end of a flight. Next slide, please. Now we're jumping into techniques that are more relevant to certification. Like I said at the beginning, it would be almost pointless to work and develop new assurance techniques if we don't also make the tie with the regulation that are being used. And so in some cases, we had researchers working on the next evolution of DO 178. So I'm talking about DO 333, for example, which is the formal method extension to DO 178. And we also explored alternative ways of doing certification. So one of those other ways to do it is to use safety cases. And bear in mind that, for example, safety cases can be used for experimental aircraft, for example. So, and at the time, it was the only technique that was available to deploy UAVs that had autonomy capabilities. So we set up to really create like a tool that can be used to easily create safety cases, to visualize what's in the safety case, and that makes it easier for the FAA to audit the safety case. So it's a lot more visual than what a safety case used to be. And there are like different components to it. Earlier in the chat, some people talk about risk and hazard analysis and the use of STPA. So a risk analysis and a hazard analysis would be the starting point of your safety case. So advocate has ways of representing this, and then you can create different types of artifacts that can be used to describe your safety case. One of those is what's called a bow tie diagram. That's what's at the bottom, at the center of the slide, where basically the center of your bow tie is the concretization of your hazard, the catastrophic event that you're trying to avoid. So what's on the left side of the bow tie is basically the barriers, the risk barriers that you put in place to avoid that catastrophic event to actually occur. So those are what you've done to retire the risk in design. It could be also the runtime monitoring that's being done early on that catches patterns, for example, way before the occurrence of the event. So those are preventions and barriers that you can represent. On the right side, you have what you're doing in terms of mitigation and recovery once that actually catastrophic event is materializing. Okay, so it's all the things that all your mitigation strategies basically to avoid catastrophic results once your event is materializing. Another thing that's important in a safety case is, or at least the way advocate is representing them, is to have a rationale for your safety case and an assurance rationale, where you start with your assurance goal and you describe basically in a very systematic way how you went about retiring or addressing that particular assurance goal. So the leaf of your diagrams are the evidences that you provide to justify that you've addressed that assurance goal. The next evolution of advocate is actually to use advocate not only as something you use before certification, but also something that you can use in operation to monitor your risk and to monitor how well you're doing in terms of addressing the risk you've identified in design, and possibly a way of organizing how you can modify your safety case to address new risks that are popping up. Next slide, please. Okay, so overarching properties, and I can see that in the chat, lots of people have lots of opinions about this. And I see that George Romanski just joined. So George will probably be able to address some of those questions in the next panel. Sorry for putting you on the spot right away. But really the intent of the overarching property was to boil down the essence of DO 178 in three, I would say, simple properties. And then say that you're for certification, provide you a path where you describe how you can address those three properties. So that's intent, correctness, and innocuity. The intent is really, did I basically define my intended behavior, and does it meet the desired behavior that I wanted in the system? Correctness is really, well, once I have that defined intended behavior, what is my argument that shows that the implementation is correct with respect to that behavior? Okay, and that's under what you're foreseen in terms of your operating conditions. And the last one is innocuity, meaning that as part of the implementation, did I introduce any extra behavior that would have a bad impact on my system? So that part, if you want to relate it to what's in DO 178, is, for example, that insistence of DO 178 on tracing requirement and making sure that no all the requirements have a path in the implementation, and that no part of my implementation is actually not related to a requirement. Okay, so really the overarching properties is meeting the intent of DO 178, but provides you a different path to certification. And I'm sure that Mike Holloway will explain that a lot better if you reach out to him. Next slide, please. All right, so I have only 10 minutes left, and I want to talk a little bit about the impact of what we've been doing. So we didn't want to just produce yet other tools and techniques that are staying in the research realm and are not applicable to real systems. So we try to work hard with industry to try some of our tools, or try the tools and techniques that have been developed under the funding, the NASA funding. So we had NRAs that we put out, and two of those were awarded to one to Collins Aerospace and the other one to GE. And we tasked them to use as many formal methods as they could on real systems and measure the impact on some of those. We also worked with Boeing, not under an NRA, but more in a collaborative ways, to get feedback on how useful the tools were. In terms of other case studies, we needed to, just because industry might have propriety concerns making their case studies available to us, we developed relevant case studies in-house. And I talked about Copilot and TC2, and also we had an internal project that was really trying to develop an application where basically we used the very formal standard process used at NASA on the space side to develop an application that was a swarm of rovers. And we tried to fold in the process some of those tools to see if they're applicable and they're easy to use or not. Next slide, please. So very briefly, the Collins and Raytheon experience, basically there were two case studies that they looked at. One was more about fault analysis, and that was on a ortho-throttle example. And then the other one was more on the control system for a FedEx engine. So that was more like the Pratt & Whitney side of the house there. So in the first one, they used lots of formal methods, tools, to try to help with fault analysis and in the ortho-throttle example. And the main results that we could see were that more faults were identified over using traditional approaches. And they they were able to characterize the time savings that occurred when they used the formal approach. Now the experience with the FedEx engine, it was a little bit, was not as rosy for our tools, I would say. So it was very complex Simulink models, and we tried to use CocoSim, and they also used the formal tool that's available in Simulink that's called Design Verifier. So they found it useful, and they could find interesting problems that would have been extremely hard to find just through their regular approaches, meaning testing and simulation. But they also run into scalability and usability issues. That actually was great feedback that we try to incorporate in new versions of the tool, and I'm sure that we'll actually use more of that feedback to improve the tools. They also used the FRED tool to try to come up with the formal properties that they would analyze on those systems. And also we have folded their feedback on a formalization of requirements into FRED. Next slide, please. The GE experience. So GE focused on using Advocate as a way of creating safety cases, and the most of their effort was spent on using the adaptive stress testing tool. And they applied it to a very tricky case because it was a flight management system. So not a trivial system by any means. So they were able to find things that they hadn't found using their usual approach for testing. And one example is at the bottom left. It's a disconnected trajectory that would be generated by the flight management system. They also realized that AST could discover events with a much greater likelihood that what they had seen before. So they were, as I mentioned before, they were really happy with the result of FADA stress, and they folded it in their continuous test framework that's going to be used on every one of their aviation products. Next slide, please. All right, with Boeing, we had like a very systematic approach in terms of collaboration. So Boeing went through great length putting together tutorials and presentation on many of our tools and techniques and presented them to large audiences at Boeing. So those audiences were about, usually consisted of more than 80 people in some cases, and you had a mix of engineers and management that are making decisions on adopting new technologies. So it was not an exercise where we just talked to researchers at Boeing. We really reached out to their development communities. Many tools were presented: ICOS, COCOSIM, FRED, Margin, RACE, MESA, Precision. So during many of those presentations, and then it resulted in really focusing on a few of those tools and working on case studies that are representative of the V&V problems that they have. So that's extremely useful to us, and we're continuing that collaboration under TC4. One of those examples is, for example, the use of R2U2, the runtime monitoring system, with a Prophecy, a tool that's developed under TC4 that does formal analysis on neural network. Next slide, please. All right. And I mentioned before, Copilot has been used in TC2. So their Copilot is routinely flown on the UAVs used by TC2 when they do their flight testing. Next slide, please. I believe that's my conclusion slide, and I'll have only 1 minute to do this. So from our point of view, TC3 was very successful. We really developed many tools and techniques for assurance of critical aviation software systems. Have we addressed all the needs? No, and we would not have been able to, because there's so much funding available, only so much funding, and the needs are really huge in that aspect. But we believe that we at least show credible evidences that formal methods can be used and can really make a difference in terms of cost, and even in terms of catching more problems if they are used at the proper time. We tried to cover all the aspects of the V diagrams, and we tried to work with industry to really show the impact. Okay. Now, like I said, we're turning our focus to autonomous systems, and we're developing even more tools. We're extending the ones that we've developed under TC3. We're creating more tools, and we're working even more with industry. We still have collaboration with GE, Collins, Boeing. We are trying to add some of the new entrants and talking to Whisk, X-Wing. We're reaching out to Aurora through Boeing. So we're really trying to address the needs for autonomy. And I'll do one more shameless plug for the workshop next week. If you're working in that field, if you feel that is where you want your voice to be heard about the needs in terms of assurance, please participate on the workshop organized by NARI on July 19th. And that's it for me. I'm 1 minute over time. Sorry, Abigail. Anjo.
Thank you, Guillaume. It's quite informative and really put a lot of meat to the chart that we showed early on. So right now what we've done is we've overviewed the system-wide safety, and we've talked a lot about the capabilities, gone through a description to provide better guidance for what's in our charts. We'd like to shift now and start a set of discussions with our panelists. We have an FAA perspective. Dr. Natasha Niyogi is going to be our moderator for this next panel, and it involves our stakeholders at the FAA. The FAA and NASA have worked together to develop tools, techniques, and processes to address critical V&V challenges for commercial operations over the years. And so Natasha is going to have a discussion with 3 FAA officials and talk about the benefits and impacts of NASA's research in the past, and potentially some of the challenges that are still unsolved that we look forward to working with them to address. Hi, Natasha.
Thank you very much for that kind introduction, Joe. I would encourage my panelists, Nitesh, George, and Steve, to turn on your cameras if you can, and we'll get the show on the road momentarily. I see all of you. So as Joe very kindly said, we're going to talk a little bit about the FAA perspective on the work that's being done. We've got 3 brilliant panelists with us who will be able to have a lively and exciting discussion. Dr. Nitesh Manikoff, Dr. George Romansky, and Dr. Steve Van Trees. I will let them introduce themselves in a moment. Before I do, just wanted to level set everybody going into this panel. As was very nicely set up by the previous presentations, the work we just heard about was motivated by an industry pull. And industry likes to tell us that the cost of doing software assurance and the current certification processes are prohibitively expensive. And of course, the FAA may have different perspectives, and we want to bring that to bear. And so we're going to talk a little bit about the work you just heard as well, bringing V&V earlier in the life cycle. So that means methods, tools, and techniques, either novel ones or even conventional ones, can be applied before you get farther down the road, before you're at that testing phase, helping to ameliorate the cost of fixing errors, as well as investigating new paths forward, which may potentially be less burdensome than current paths to certification, such as safety argumentation, and of course the overarching properties, which have been mentioned very much in the IO interface. And we've got a couple of overarching property experts here, so we'll hopefully be able to get to some of those questions. And another thing, just before I jump into the introductions, of course, NASA and the FAA works very well together. We have something called research transition teams. And so I think most of the folks on this panel have at one time or are currently serving on a research transition team, which helps to see some of the work that NASA does get pushed out either to industry or to the FAA. But with that, I want to jump in and let my panelists introduce themselves. Could I have Nitesh go first, then George, and then Steve?
Definitely. Thank you, Natasha. And thank you NASA for inviting us. First of all, congratulations to you all. James Webb, a mind-blowing engineering feat by NASA. It's a wonderful day to have a conversation on system and engineering assurance. So the perspective which I would like to bring is informed by the roles that I have played in our collaboration. I'm currently the Chief Data Officer at the FAA. Prior to that, I was the Chief Scientist for Software on the Next Gen program, and had a wonderful opportunity to kind of collaborate with you all as we were thinking through the technologies for improving assurance practices as we build systems. I caught a piece of what Guillaume shared. Looking forward to conversations on those things. If I had to pick one challenge within all of these things, is that within aviation, within aerospace in general, the pace of change has increased. So the practices that we had to assure safety critical system deployments, while they are robust and have served us well before, they don't keep pace with the pace of innovation. And so many of the tools which you have discussed, Advocate, ICOS, or several of the tools that Guillaume described, will improve our ability to kind of keep up, or at least make some headway, and not fall behind in introducing these systems. So the significant challenge I see is that while these research tools are extremely helpful in specific areas, without those actually getting transitioned into the practitioner's hand, the promise just remains elusive. The expertise needed sometimes to actually apply many of the tools that NASA brings to the table in the commercial kind of environment is really difficult. And I'm not really speaking for the areas of expertise that George and Steve will bring. I'm talking more from the NAS automation side of the world. So looking forward to the conversation. Hoping to hear what Steve and George have to say.
Hi, so my name is George Romansky. I'm the Chief Scientific and Technical Advisor for aircraft software at the FAA. One thing I would like to stress is, how pleased I am to be on the RTT team. I found the collaboration to be really important for me. It's important to learn from each other. Software for me is a narrow field, but it touches so many automation systems. And it's by collaboration, by learning how other people are doing various elements of AAM or any other field, that I learn more and I'm better able to help the FAA, which helps the FAA in turn. So at the FAA, we have a good safety record for Part 25 planes, and we use DO-178C almost exclusively. But now we're seeing a big spectrum, and I know that Steve Van Treese will talk about this a bit more. But when I start looking at the level of rigor required, I see that there is a difference based on our safety continuum, where speeds and size, speed, or kinetic energy of vehicles makes a big difference. So the thing that I look at is the software, the control monitors, the control systems, and I see that risk covers a very wide spectrum. And unfortunately, our software guidance documents that we currently have don't have that same spectrum. They come in steps. And there is a huge difference between level C software and level D software. And when we start developing software and verifying software at level C, we find that costs are much higher than people expect. And it may be because we're doing too much, because we don't have in-between levels and we can't partition between the levels that we currently have. So that's why I like the approach. We've heard mentioned the overarching properties, and it allows us to build an argument where the argument gives us a certain level of flexibility. The argument can reference out other DIA 178 artifacts. So it could be that you could use the overarching properties and DIA 178C, and then use the argument to present the evidence that you have, to present the artifacts, rather than go through a descriptive document where you have to find the evidence yourself. The argument structure could be novel to cover novel approaches. And in particular, I like the idea of using overarching properties and the arguments to start covering things like artificial intelligence and machine learning, because that gives us the flexibility to come up with a persuasive argument that this is adequate, this is good enough. So it's a way of presenting trust. Now, one could say, well, how come we can trust the system based on an argument? And I like Mike Holloway's quote, and he says, you know, trust, basically, if anyone who needs to believe the argument believes the argument, then you have a trusted system. So that's the definition I'm going to use from now on, because I think that's if you need to understand it, and if you do believe in the argument, then we have trust. Now, we have people complaining about certification costs with DIA 178, and people have invested a lot of money in development tools, but they haven't invested so much in verification tools. Now, when I go into an audit, I'll have the big Part 25 type applicants, and they bring in 6 or so, maybe 5 or so engineers to help support the audit. I said, who are they? And he said, well, this is the guy that knows about the requirements repository. This guy knows about the design repository. This guy knows about the source code. This guy knows about the test. And this information is now stored in different repositories, which means that information is now linked, but very indirectly, but it's still linked. By regulations, we need traceability between evidence. We have the traceability, but it means looking at this repository, picking up a tag, doing a search in this one to find that link. That's what increases people's costs. That makes life very expensive. If you have the information, if you have it all linked together in a repository, why not just do traceability as part of that process? Why not do impact analysis as part of that process? Yeah, I think it's nonsense to try and split it up in the old-fashioned way of doing either spreadsheets or spreadsheets implemented via databases. It just doesn't make sense. It increases your costs. I'll stop for now, and I'll hand over to Steve.
So Steve, you're still on mute.
I am.
That's better.
Thank you, George. Now I'm here on the shoulders of giants. I'm Steve Van Trees. I'm a senior engineer in aircraft cert. Been there the last 25 years. Early in my management career, I was the first manager at the FAA to have UAS in their remit. So it's been around UAS a long time, and so I'll start speaking to my slides. The idea is I want to focus a little on UAS, on the uncrewed aircraft, and talk about some of the challenges in looking at them. And I think George just mentioned it, that a lot of these are much more on the verification side. Are you trying to decide that you're building the right thing rather than that you built it right. Generally, we trust people to run down the validation side to, there are very few kind of errors in code. It's the errors in the top level requirements that causes trouble. And so the idea is talk about 5 things. One is architecture. The other is the some specific remarks about detect and avoid and command and control. There we are. Some questions about failure conditions, and then want to look at the work going on in the FAA in associated elements, so that the some novel ways the FAA is looking at approval of UAS. So if we could go to the next slide, we have the one challenge we posit for command and control and DAA. So up in the top right, we have the traditional triangle. We have the aircraft components themselves. We have the lost link procedures, and we have the quality of the link themselves. And the insight is the 3 of those work together, and you can make trade-offs between each of those. So we have successfully encouraged that we can't build communications links to infinite level of development. We can't. If we could, we couldn't afford them. So that the idea of validating your lost link procedure and the level of automation on the aircraft is the way to go. The bottom left, if you think about detect and avoid, which is kind of a corollary to command and control. If you've lost your link, then you're in a detect and avoid situation. And we one of the early insights, right? One of the things we've always been striving for is an automatic detect and avoid, that we don't need remote pilot interaction at these levels, especially for the smaller UAS. And one of the things we're looking at, especially in the bottom left there, is some of the newer UAM kinds of applications. You may have very different DAA requirements depending on the phase of flight that you're, takeoff and landing. You're very much like a rotorcraft requirement, and level flight. That's something much more traditional. But it is very different from the way we did TCAS or the way we've done DAA. So next slide. So the one of the elements here is we have been approving the smallest UAS, the durability and reliability UAS, and the insight has been that aircraft cert has aircraft in its name, and we had kind of forgotten that until we looked at the regs. And so that the aircraft cert is responsible only for that type cert boundary there, the boundary that defines what the aircraft itself does. And so we have been successfully reaching out to other disciplines in the FAA that things that are on the ground will be much more in an operational approval perspective that from flight standards or from air traffic. And if you turn the page looking at our approval, this is next slide. This is a famous slide that I took from Wes Ryan of NASA last week, because he took it from me some time ago. So it's it's now research because it has plenty of citations. But the idea is that the associated elements work seems to have backed into something we had been trying to do in safety assurance between NASA and the FAA for some time. Okay, so that you can't just take the aircraft software and develop it to as many nines as you want. That you must involve the operational safety perspective, and as we said, the lost link procedures and such. So it's much more an issue of distributed architecture than it is putting all your nines on the aircraft. And what has happened is something that we have been trying to do between NASA and FAA for years has fallen into our lap in terms of that opportunity, that we now have to do it the way we wanted to do it. So I thought that was a very nice juxtaposition. And so the next slide, please. Good. So again, this is again in the nature of NASA FAA dialogue. This was a designing for straight to autonomy. So one of the issues we've talked about is the level of automation on an aircraft, and one of the old chestnuts between the FAA and NASA, the idea that you're going to have levels of autonomy, and then your failure case, you're always going to have a human backup. And I have always said, from an FAA hat, that I don't understand how that paradigm works. That if you're at a sufficiently advanced level of automation, and the automation fails, you're going to give it back to the pilot with less control service and less flexibility than they know what to do with. That is not really the way to do it. So this top slide is again NASA. It's speaking and talking about how we really look at the very significant rules for UAS, the well clear, the collision avoidance rule, and how we work that under validation to look at how autonomy and how the human factors work in there. And I think there's still lots of work to do, and I look forward to being back with Natasha on the RTT to explore some of these. So that's my time. Thank you.
Thank you all. Those were great introductions. So with that, we'll jump into a first question to get the discussion going, and then we'll begin pulling some questions from the audience. So just to kick us off, we've heard a lot about means and methods, tools and techniques in some of the previous presentations that are being developed by NASA or being developed out there. What do you think the biggest barrier is to applying new means or methods, tools and techniques to the verification, validation, and certification processes for aviation systems? And I will let whoever wants to jump in and start that off.
I can jump in terms of major barriers. Over the years, what I alluded to this in the introduction, and Natasha, the complexity of these, of what we are trying to do, whether it is with the verification tools or the concept validation and requirements validation kind of phases, requires pretty sophisticated tool suites, and NASA is developing many of them. In many cases, transitioning of those to practice requires a lot more tooling around them for those to be effective. And I would say that you all, R&D has done a great set of foundational work to ease the path, RAISE being an example. So there are some foundational things which are needed if practitioners are to adopt what is being proposed out there and the tools which are being released. Guillaume did kind of talk through how we have been assessing impact of these tools and how it is getting out into the marketplace and who is using them, and the recent work with Boeing to kind of see adoption, because none of these tools are very useful if they stay in the research labs. We don't see the benefit of those things, right? So we might be proving the theoretical value of these things, and some small group somewhere that is not communicating with us is benefiting from them. If we don't get visibility into it, we cannot advocate for more investments in these things. So a necessary work, I think, has to be figuring out how to educate practitioners. The feedback loop of trying to identify which tools are more important is clearly a need, and I think that work happens. But how do we make sure that it gets into their hands and that they are able to use it and they're able to benefit from it and have that virtuous cycle where that feedback comes to NASA and you get the signals to understand where exactly should the research be pushed? Because I think that's the value of the conversation in a group like this, to kind of try and understand. If you go to some of the GitHub sites that in the past decade, NASA started open sourcing some of these things, you will not see the kind of adoption and contributions coming from the industry. So if we want to kind of build on the work of each other, we have to figure out how to make that more active, because otherwise there is no signal back saying that these things are actually getting adopted significantly. So there are lots of barriers. This is one I would kind of keep beating the drum about.
So I see a problem which is, well, maybe seen as an FAA impediment, really. Under our regulations, if you want to use a tool, the tool has to be qualified. But tool qualification is done on a project-by-project basis, which means that a tool vendor can sell a tool, but that tool has to be qualified for a particular project and then audited and approved for that particular project as part of that certification. It seems nonsense to me, and it seems the best approach would be for us to have a process by which tools can be approved independent of the project, which means that there could be a market, people who develop tools, tool vendors, but they could develop the tool along with a qualification package that could be automated and run. In other words, you can buy the tool, you can buy the qualification package, you can run it, and if it passes on your target platform, then the tool is qualified by definition. And to me, that would start opening up many more possibilities of people. I mean, there's an incentive now to develop a tool with a qualification package, because it can now be sold on many projects quite easily and be used by people quite easily, rather than have to wait for an auditor to come and approve the qualification data. I'm surprised it's not here yet.
In some cases, it doesn't quite fit in NASA's kind of mission space to kind of figure out how to get tools qualified. But if we want to see rapid adoption of these things, we'll have to give some brain cells to that particular problem too.
Steve, I think you're on mute.
That's what it says. I think the other element, one of the we had mentioned the challenge of matching aircraft cert and operational approval, and I think with the direction UAS approval is taking, I think there's a real opportunity there to explain what design approval thought it was doing as far as mapping into the operational approval, because some of the things that are now sitting on the ground used to be nominally aircraft cert artifacts and are now not under our jurisdiction. So we will we would certainly contribute. We would certainly do, design approval guidance, but we are not the final approval. So stepping into the picture we gave in that slide, I think would be a real opportunity.
Natasha, can I just add something to what Steve said? So the operational approval process, again, you all have done great work, advocate, so safety assurance, safety case, and speeding up safety case analysis there, and tools like Advocate for that. To Steve's point, the operational approval, where all these independent components have to kind of be stitched together to make that assurance case. I don't know of how FAA thinks about adopting those practices, so we need to do a little bit harder kind of. We need to push a little harder there in our RTGs on those things.
Definitely, I think that's a very important point that will lead me to. I was going to pull a question from the audience, but instead I'll jump to a question which follows right on to that, and then jump to questions from the audience. Some of the things that both of you were, Nitesh and Steve, were just talking about. How might you see some of these, means, methods, tools, and techniques that are being developed being applied just beyond, vehicle certification? So, this can mean to ATM, to infrastructure, to the larger question of that integrated operational design approval. So any thoughts that you might have going forward on that?
Okay, George, you want to jump in?
So we have, just for your information, we have an incentive. Well, we have a project working actually the other way, where the FAA wants to start using other standards, for example, automotive standards. There are many people developing battery technology for cars, and they're spending a fortune developing this and certifying the control systems and the controllers. And we would like to be able to use those inside a UAS. Unfortunately, they're developed using ISO 262 and not our standard. So what we've done is we've looked at DO 178 and DO 254, and we've extracted and what we call the abstraction layer from it. In other words, we've captured the essence of what we'd be looking for in a certification. And now what we're doing is we are going through and mapping that abstraction layer onto ISO 26262 to see if ISO 262 satisfies our requirements for aircraft certification. During that process, we may find some gaps. We may find one or two things that are inadequate, but we can take a whole package developed by someone else, and if they can give us their certification data they've developed, we can look through that data, and then we can say, well, there's one or two gaps that are missing. Can you please fill them in? And then we can approve the complete certification. In other words, we're looking at alternate standards that we can apply. And while we're using the automotive standard to start with, it may be that we could start taking NASA standards or industry standards and try and merge together, and then have a mechanism by which you can use many standards to accomplish, which is essentially, it's the same thing.
Just to different perspective. So George is obviously, I'm not going to get into the certification side of things, but operational approval and the safety risk assessment part of that. I think there's a lot of room for FAA, and not laying this on NASA and NASA research, to really adopt model-based systems engineering. And George kind of alluded to our current challenge of not being able to link these things when we really should, to really kind of take the model and iteratively kind of get assurances out of them, not just for the specific case that George mentioned in the certification side of the world, but in our complex operations as well. So digital twins for air traffic management and the NAS itself would be a place to go for some of the operational approval cases that we would want to think about. The other aspect which would really help, as you know, when you think about testing any of the automation platforms which go into air traffic management deployment and adoption, the tests, the state space is too huge, right? And truly exploring the high risk aspects of that needs a lot of improvement. Currently, a lot of that is dependent on human judgment. We do rely on modeling and simulation to a great extent, but there is a lot of improvement I think we can make in that area of kind of guiding the process of testing and verification to kind of speed up the process and reduce the cost for everyone involved. Just a little, NAS perspective there.
I think the other element that's been mentioned is to keep the safety case in mind, keep the architecture in mind before you get down to the levels that we work with flight standards, we work with air traffic. There's a lot of operational experience, operational wisdom there. We don't have to do it all on the aircraft itself.
Excellent point there to sum that up. With that, I'm going to jump to some audience questions. And there are a lot of audience questions concerning these mysterious overarching properties. So I'm going to ball a couple of them up and probably offend all of the askers and direct the first shot at George, because I know he'll have a comprehensive answer, and then Steve and Nitesh can poke holes in him if they feel like it. So in general, people are asking about how to use the overarching properties is how I see it. Some folks see it as a means to support regulatory approval and not necessarily establishing safety. And so they're wondering, how do you show that satisfying the overarching properties is sufficient to establish the safety of the system? Does it capture all of the interactions between humans and the system? Also looking at how does this relate to creating perhaps, a safety case? Are the two equivalent? So I think they're really looking for a little bit of background on, how the overarching properties came to be and what they're hoping to gain from applying them.
Right. So the idea with the overarching properties is having the three properties is basically the framework, but really it's a framework to construct a set of arguments, and the arguments are safety driven. So we do look at the system and we try to extract the safety properties of the system, and as we extract those properties, we can start constructing an argument. And by constructing the argument, we're having a premise, we're having basically the argument structure, and we can even have defeaters. In other words, where you can look at an argument and then you throw in, said, well, what if this happens? So you can put in a defeater and see if you can defeat the defeater, as it were. But you can build up a set of arguments, and it's building up a set of building up a trust. Now, I'll give you an example from many years ago when I did a security analysis for robust partitioning. And the problem with robust partitioning is that what you're trying to do is to show that one component cannot affect another component unless it's allowed to. And these are negative requirements, and it's extremely hard to prove or show negative requirements. So it was extremely hard to show, well, this component, this module will not be able to write into the memory of this module, and this module will not affect the timing of this module. What you can do, though, is you can start building up an argument and say, well, the interactions can be either memory, they could be time, or could be use of shared resources and so on. And then you pick on one, and let's say I'll pick on memory. Well, memory can be partitioned into read-only memory, or can be cache memory, or could be RAM. And you start building up an argument and you say, well, how do I show that this cannot write over there? And then you say, well, if I set up a memory architecture, memory protection mechanism that will only make this visible while it's running and make something else visible while that's running, then it's not possible to write into the other guy's memory. So now you see you're building up an argument and not just testing to saying, well, under these conditions, I can't write over there, but I've built up an argument saying I've constructed an architecture. The architecture is using some hardware, and the hardware has been tested to show these various properties. And we've built up an argument to convince us that these properties are what we're looking for. And you can do exactly the same thing for software components or hardware components and so on. You build up a tree-like argument, and then you make sure that that complete data structure, that tree structure, is compelling and convincing. And that's how we see arguments being used. And when we come and audit, the argument should be easy to understand. If it's really complicated using formal proofs and mathematics that the auditors don't understand, then it's useless. It needs to be easy enough for the people who need to be convinced that the argument is sound. Hope that answers the question.
We'll let Steve or Nitesh comment and add anything they want.
I don't think I can add anything to what George said.
I think George is exactly right. In all seriousness, you've got to get the FAA auditors to understand what it is you're trying to do. If it's too formal, you spend all your time briefing the tool and not the result.
Well put, George. I'm going to attempt to ball up another audience question related to seeing the use of tools in the wild, in industry. So can any of you remember or speak of an example where you've seen perhaps a formal tool like a theorem prover, or another, kind of a tool like the ones that were mentioned, so model checkers, theorem provers, means of requirement specification like FRET, being used and perhaps being used to gain credit in an actual certification application, and if so, tell us all about it, and if not, any thoughts why you think that isn't. It kind of relates back to question one, why that isn't happening.
Well, I haven't seen all-encompassing tools that cover everything. However, I have seen tools focus on specific properties. So, for example, there are tools that will look through the source code to make sure there are no out-of-bound accesses. It's the usual problem if you have an array and if you access outside of the array, you can corrupt something which is not yours. And there are tools that will do boundary analysis that will then check for those boundary conditions. And those are good properties to check. Now, it isn't complete. And I know code review is still required because we have to make sure the code satisfies the requirements or the stated behavior. However, there are properties during code review that we look for to make sure that these errors are not put in by mistake. Those types, I've seen those types of tools used quite successfully.
Just to add to that, Natasha, so definitely not from the certification side of the world, but for air traffic systems, tools like ICORS do get used, but the attempts which we made to see if our technical partners would adopt these specific tools which came from research were really problematic because they wanted to use tools which applied in lots of different cases. They didn't want bespoke tools which applied only to one team in their organization. So they're going to look for actually slightly lower capability tools, but which can be used by a broad range of their teams. So hence the adoption stuff needs to kind of think through, how do we get that, I mean, to Josh's earlier point about how do we get that into the commercial space where folks who are building software for FAA, again, I'm not talking aircraft and certification side of the world, how do they more easily figure out ways to adopt these things? Because they're not just trying to gain credit for certification, right? They're trying to reduce their defect cost. They're trying to get faster development. They're trying to reduce the development cost. So these tools can be enormously effective there, but it has been hard to find true adoption. It might be that it's happening, but it's very difficult to get evidence of it.
Yeah, I would agree with what George said. I would pass on that one.
There was one particular tool, if I could mention briefly. I used a tool, I can't even remember the name, but many years ago, and that was to try and do schedule detection and scheduling in a real-time system. So I took the tool and I thought I'll try one example first, see if it works. And I put in the dining philosopher's problem. And the tool was very good. And it took me about 3 days to put the problem in because I had to learn how to use the tool as well. But I put the problem in and it detected under which conditions the dining philosophers would starve and detected how you could, or proposed how you could resolve it. So I was very pleased. But then when I looked to see how much work it would be to apply it to something like 20 or 30 tasks, then it just became too much work. It's just too much work to try and do that. And it only gave me a good win, but it was a very narrow win.
Well said. The usability and scalability of tools are always a concern. And so one thing to mention is, has anybody heard of or seen a tool that can, for instance, help with hazard identification? Is a question we're getting from the audience. So any thoughts? I can see George smiling already, so I'll let him jump in and give a thought on that before we close out with everyone's summary statement. Go for it, George.
Well, it's hard. It depends on the hazards. You know, if you're looking at, so I've seen people propose analysis tools for security risks or security hazards. But I haven't seen, in general, I haven't seen hazard analysis tools being used on software. And the sort of hazards that I was looking for are much deeper inside, and it's difficult to quantify them and to analyze them.
Not exactly a tool for hazard identification, but consistency of application of those identified hazards across use cases, we find has been lacking. So, things which are done 2 years before, folks go and come up with slightly different analysis 2 years later. So tools in that space, and these might be really simple tools to kind of ensure that we are building on top of prior work in a consistent fashion, and it's not just left to judgment in some cases on the operational side. Those, and this might be text analytics on safety analysis documents and so forth. I think there is room there.
So there is one tool that I used a lot, and that was a linker verification tool. So once you've constructed software, lots of components, and you link it all together, how do you know the linker has built the right thing? And normally if you say, well, we can test it, well, the testing won't find the sort of errors. So in looking back over many years, there was one error that was found that was really quite profound, because what happened was that there was a library and there was a move function in the library. And everybody used that from the operating system. It was a move, but there was a new guy came on and he wanted a faster move. So he wrote his own move. And it was fine for his piece of software. It was linked in and it was perfectly fine. He used it. Now, his move was faster because it assumed you didn't have overlapping strings. So if you move not overlapped, that's fine. You're moving from here to here. But if it's overlapped, then this one starts writing over the tail starts overwriting the head, as it were. So move overlapped is different from move, but he called it move just like the other one. Now, the one in the library was the safe one. It would work out if it was overlapping string. The other one wasn't. And unfortunately, the linker chose the first one it came to, and it depended on the order in which you presented the components. So there was one time where the component was mismatched. Unfortunately, we found it. Fortunately, it wasn't a risk anyway, but it could have been. So my check has always been make sure that there's always that all the names in a link map are all unique. A very simple check, but that'll find that sort of error. Very simple tool, used it all the time.
Excellent.
You know, you get bitten once, you're careful.
Yes, regulation is built on scar tissue. All of the things you've seen gone wrong, indeed. Steve, I was wondering if I could start my closing statements with you, and we could go in our backward order just to get any of your thoughts out there and last things you'd want the audience to take away.
That would be good. I'm fine serving as the warm up for this this distinguished finale. So I think one thing we've observed is that, you know, as UAS gets smaller, as aircraft get smaller, we have pressures both to do things that are of greater risk and to do things, as George mentioned, at lower cert developments. And I think the only way to do that is to look at a couple of things. Look at the architecture, look at the hazards. What we really care about is how badly this thing fails, and especially to look at the environment. And that's very hard to do, but really studying the way the characterization of the airspace and the characterization of Nitesh's work of the NAS is just so very important. One thing we tried to do in RTCA, and you mentioned scar tissue, we tried to just do MOPS, which are just these little standards, and then finally decided we needed to build a mass for system spec to say what it is we're trying to do before we decide levels and everything else. We had to learn the lesson I preached today, and that's been very powerful for us. So we look forward to continuing to work with NASA on this real challenge. So I'll hand it to Nitesh.
Thank you, Steve. And thank you, Nitesh and team, for having us here and for this conversation. First of all, I want to thank everybody involved in the tool development. We talked a lot about challenges associated with it and barriers to adoption and so forth. But there aren't a lot of people doing work in this building of VNV capability space for safety critical systems. I've always felt that if we could find like-minded industries, we could probably find incentive for tool vendors and all to invest in this. So the automotive industry kind of linking up arms with us and so forth is really helpful. Anyway, so thank you for the good work in the space. This is about the transfers. A lot of good transfers happening to industry. We haven't been truly successful in having a lot of the technology we discuss here today into ATM related activities. There's a lot of potential there, and foundational capabilities like RACE, and if Mesa is built on RACE, those kind of things are, I think, worth investing in. And we should continue to think about these complex adaptive kind of systems, which we are now encouraging with Steve, UAS's urban air mobility. All those things will require us to not have a very static view of the safety case, but keep getting informed by operational feedback on what those things are and continue to kind of adjust and measure and adapt. So looking forward to the tools kind of helping us get there. We are always a little slower than what the world wants us to move. These tools will help us reduce the cost and time needed to kind of actually move. So thank you for the opportunity for this conversation.
Yes, thank you, Natesh, and thank you, Natasha, for inviting me. And the way I look at it, we have a lot of challenges. The complexity of what is being constructed is growing at an alarming rate, and the volume is growing at an alarming rate. While we might seem that, the UAS, the small UAS, that's fine because it's only a small thing, but if you have 100,000 of them flying in the air, then it becomes a big thing again. So the other area I look at is UAM, where we have different modes, different paradigms now. In the Part 23, we had a pilot. So we had some automation. We had a pilot who's an intelligent controller or intelligent monitor. They'll take over if something goes wrong using direct modes. They don't exist in the new UAM markets. So if the systems fail, then we have a bigger problem. However, I feel that with the cooperation with NASA and FAA, the various teams cooperating and working together, I think we can discover and co-discover these problems between us. And as long as we keep sharing them, then we can stay ahead of them. It's only if we try to zoom off in one direction, then that's when we fail. So I really enjoy this cooperation.
Thank you all. I really enjoyed, took a lot of notes, a lot of writing. Really appreciate the time, and Natasha, thank you very much for leading this interesting panel.
No, I think all of our success is due to Dr. Manikoff, Dr. Romanowski, and Dr. Vantrees. Their wisdom has definitely enlightened me. I've taken a ton of notes as well. So thank you all to our speakers. You guys are great.
Thank you.
Thank you.
Thank you.
I did want to make a note that there are a lot of questions, and although we didn't get to all of them in this panel, there is a Q&A at the end of the day at 4 o'clock, and we will try to address them there. And if not, you can email Abigail, and we'll forward the questions to the appropriate parties to get them answered. So please continue to use the conference IO for questions, and they're important, and we will work to get them addressed either at the end of the day or offline in the near future. So, yeah, so we're going to go to our next panel, which is going to be led by Guillaume. He's a moderator, and this is a panel we've heard from our FAA stakeholders, but the FAA and NASA aren't the only two entities working in this problem space. There are other peer organizations to NASA doing research, and we were curious about their perspective on tools in this problem space, and we also collaborate with them to be aware of the research that they're doing, and avoid duplication, but also work off of lessons learned, and we cooperate and collaborate with them in conferences, workshops, and as peer scientists. So Guillaume is going to lead a panel discussion with our peers on automated V&V capabilities and hear their perspective. Guillaume, thank you.
Thanks, Joe. You kind of stole my thunder. What am I going to say now? You said everything. Yes, early on in TC3, we talked to other government agencies to inform them of what we were planning to do, and to also see if they had needs that they wanted us to address. And it's not necessarily the person you will see on this panel, but that'll be interesting to see what they think about what we did now after the fact. So I'm going to introduce very quickly the people on the panel and let them really introduce themselves after that. I want most of the time to go towards our panelists. So we do have Rick Kuhn from NIST, Brad Martin from DARPA, Duan Civilian for NTSB, and Laura Humphrey from AFRL. I think I'm seeing Rick appearing. Let me see. Laura is here. Duan is here, and we're missing only Brad. He might have connectivity issues, from what I'm saying on the chat. So I'll say that we will start with the three of you, and hopefully Brad can join us as soon as possible, right? So being from French origin, sorry guys, but I have to let ladies go first. So.
All right, I guess that's me, huh?
Yeah, Laura, you're it.
All right, so my name is Laura Humphrey. I work at the Air Force Research Laboratory within the Aerospace Systems Directorate. I work in what's called the Autonomous Controls Branch, and I am a team lead for a small team that is focused on approaches to verify and validate autonomous systems. So in particular, we're doing a lot of formal methods. I got involved in this when I first came to AFRL. My PhD is actually in control systems, and so I think this is an interesting panel for me, because what I was told is that we're sort of wrapping up technical thrust from NASA on software verification, and not necessarily yet looking at future autonomous systems. But I came in actually looking at future autonomous systems. I joined a group that was working on autonomy for teams of unmanned aircraft. So this team develops like a lot of algorithms for what we call cooperative control. But then, the question came up in the Air Force, okay, implementing these algorithms is going to bring a lot of verification challenges. What are we going to do about that? And at the same time, what I've seen within AFRL is it's very challenging to develop these algorithms and sort of have arguments of correctness. That doesn't mean that the software problem isn't still hard, right? So as we implement these complicated autonomy algorithms in software, all the software verification challenges really just become harder. So I ended up investing in learning formal methods, and so I have done a lot of research related to various applications of formal methods. Also looked at some applications related to human automation interaction. So I have a pretty strong background on model checking and probabilistic model checking for multi UAV or vehicle controllers, for mission plans, either autonomously generated or human generated. I've done some work on correct by construction synthesis for things like discrete logic controllers. And then, like I mentioned, we've gotten interested in, as we take these things into software, how do we verify that the software is correct? So some things that I've worked on, our team has not developed as many verification tools as NASA has, but we are applying some formal verification techniques to our autonomy framework for so autonomous control of multiple vehicle teams, which is called OpenUXAS, which is available on GitHub. And then I mentioned correct by construction synthesis, so I contributed a bit to a domain-specific language for doing certain types of synthesis called SALTI. I will also do a quick plug that if you are in academia, we do have some academic collaboration opportunities through what's known as the AFRL Summer Faculty Fellowship Program, and also through NRC. And so I have links for that there.
Thank you, Laura. And I can testify they have a great setup to welcome people and work on case studies. So if you're out there, take advantage of it. All right, where do we go next? I might be driven by the slides, or if I don't have an order, let me pick at random. How about you, Duan? I worked mostly with Dana, but I'm sure she briefed you on our previous interactions.
Absolutely. My name is Dewan Stavillian. I'm a senior human performance investigator for the NTSB. And my focus primarily at NTSB is investigating air crashes that involve system safety related issues, certification, and human factors. So we've seen over some years a lot of issues in that space. But prior to NTSB, I spent many years in the design and integration part of aerospace related to system safety and certification. So developing the designs and so on. And so we're encouraged, NTSB is encouraged by the work of TC3 NASA, especially from the verification and validation of systems and software. Because when we look at accidents, we definitely go down that route in terms of viewing that those issues. So today, I just want to discuss next generation aircraft system design and integration challenges related to system safety and certification, including these issues in the aircraft accident investigations. So for many years, the NTSB has investigated aircraft accidents and developed safety recommendations to improve aviation safety. Probable causes to accidents have been related to operations, systems, maintenance, and human performance. But as the NTSB continues to investigate these types of accidents, investigators need to remain vigilant of new and modified integrated system designs, failure modes, and operational history. Software safety and related certification issues are also important, especially software design complexity and its effect on pilot performance. But with respect to accident investigation, investigators typically examine system requirements, design and integration, verification and validation processes, so that investigators can understand any shortcomings or success within the certification process. So as those new and modified systems are developed, an understanding also of any bilateral agreements between regulatory agencies is also important, including how we share certification data related to system safety. Next slide. So recent oversight in the aircraft certification processes has led to changes in the way airplane manufacturers certify aircraft. The Aircraft Certification Reform and Accountability Act has shed light on airplane certification issues, including a review of methods to identify, analyze, and manage safety issues in certification. But furthermore, the Government Accountability Office, they recently published a report on aircraft certification, which evaluated US and European agencies' certification procedures. So NTSB is encouraged by these industry initiatives that are aimed at enhancing the safety certification process. In terms of the recent accidents, the 737 MAX accidents, we know that those are indicators that design, integration, and certification of systems are critical to aviation safety. The NTSB's investigation of a recent airline accident revealed that system safety and certification continue to be emerging issues in aviation safety. So I want to highlight an accident here. October 17, 2019, Pin Flight 3296 was involved with a runway overrun that killed one passenger and injured many others. And the investigation found that an anti-skid brake system failure mode was not considered in the certification process, which was a factor that had a negative impact on the crew's ability to successfully stop the aircraft on the runway, which led to the overrun. And investigators noted other system and software safety related issues with the anti-skid system throughout the investigation. And engineers' design assumptions need to be critically reviewed by the company and regulator for accuracy. We wanted, to ensure that the failure modes and effects on the system and airplane are considered, including the mitigation of those hazards. So many of us are familiar with functional hazard assessments. But as the NTSB continues to investigate aircraft accidents and incidents and related system and software safety issues, there needs to be a focus on these areas. And as manufacturers develop and design advanced aircraft systems, aerospace companies and regulators need to have a laser focus on design and certification processes and many of the impacts it could have on aviation safety. Next slide. Thank you for your time, and I look forward to the discussion.
Thank you, Duan. Let's go to Rick, who might have a slightly different perspective because I think you work with a different industry also, right?
Yes, thank you. So I have one slide. Is that available there? Yep. Okay, so yes, as this says, NIST is the nation's measurement and testing laboratory. Our mission is to do research in better measurement and test methods and get those out to industry. This project has been focused, that I've been working on, has been focused on combinatorial methods for better measurement and testing. And as Guillaume mentioned, this applies broadly across a variety of industries. We have users in many different industries. What we're referring to is basically an outgrowth of the field of design of experiments from statistics. So rather than doing orthogonal arrays, we do covering arrays that cover T-way combinations. So in other words, all two-way combinations of input variable values, three-way combinations, four-way combinations, and so on. The reason for doing this is that we have some very solid empirical data that show that the number of factors involved in failures is small. Most failures caused by one or two factors, a few more by three, and very few by 4, 5, or 6-way combinations of factors. And so far, we have not seen, and as to my knowledge, others have not seen failures involving more than 6 factors in the field. So the reason this is useful and interesting is that it means we can do what we call pseudo-exhaustive testing. We cover combinations of factors. So for example, if we know that all failures are caused by a small number of factors interacting, and we test all 4, 5, 6-way combinations of these values, then we've done something that's in some sense equivalent to exhaustive testing. Obviously not truly exhaustive because we have to do discretized values and so on. But in practice, it's very effective. We have a lot of empirical studies, and others have done lots of empirical studies showing that this is very cost effective for strong assurance. We distribute a tool that is widely used, especially in aerospace. Our first early major user was the Air Force Test Wing at Eglin Air Force Base, and they have done and continue to use this extensively. And now it's spread to more than a couple thousand organizations. We've also worked quite a bit with the NASA IVNV Katherine Johnson facility in Fairmont, West Virginia, and the Air Force Institute of Technology. So we have done not only test tools for covering these combinations, but also for measuring the combinatorial coverage, measuring the coverage of the inputs. Earlier, Guillaume mentioned the importance of testing corner cases. And so that's something that falls very naturally out of these methods, because if we cover, say, all 4-way, 5-way combinations, then we will get the corner cases. And we can also measure the coverage, the combinatorial coverage of tests that are developed through other means. It might be interesting to try and measure the combinatorial coverage of something, of test sets produced by, so the ADA stress testing tool mentioned earlier. And real quickly, just a few of the high points of the work that is produced out of joint work with others. At the Air Force Test Laboratory, we developed jointly with them something called sequence covering arrays, which is something that had not been previously used in testing, but very effective, efficient coverage of test sequences. Also solutions to the test oracle problem. And this has been used, this method has been demonstrated, for example, by Rockwell Collins has used it in showing how we can generate full tests that meet MCDC coverage for FAA level A. And this is from specifications, so not from the code, of course. And finally, input space measurement. We want to measure the coverage of combinations that are included in tests. And this is a very valuable thing, as we mentioned earlier, for conventional software. In fact, this was developed to measure coverage of some NASA spacecraft software developed at Johns Hopkins Applied Physics Lab. But I would argue that it's also really essential for autonomous systems, especially that use machine learning black box algorithms, because in those cases, the structural coverage methods don't apply. What we really care about is the degree to which we have covered the input space and the degree to which we can handle all of the inputs that might occur in practice. So we want to measure the combinations of input values that are covered. And so that will give us a good sense of the effectiveness and the accuracy of the software. So thank you.
Thank you, Rick. That's interesting because the very historical initial research on margins was actually based on combinatorial methods. So we did explore some of this before moving on to more mainstream statistical analysis type techniques.
Interesting.
Let's try to see if we can get Brad. I don't think Brad is going to be able to show himself on the camera, but he should be able to talk to the slides. Right, Brad?
Hi there. Again, sorry for the camera access sort of issues. But again, I'm Brad Martin, currently serving as a program manager at DARPA on loan from the National Security Agency. So regarding my role at NSA, I've served for several decades within NSA research, where I've focused research and research groups in the areas of verification and validation with a perspective on designing, architecting, and analyzing systems in support of evidence-based trustworthiness or trustworthy systems. Coming to DARPA, DARPA I2O, I've continued this interest with goals of enabling high assurance pipeline software systems engineering, including integrating and scaling formal methods for the purpose of facilitating rapid and continuous delivery of emerging capabilities to the mission with a focus on T&E, so continuous, confident, and affordable T&E. At DARPA, I've been focusing on designing systems for cyber resiliency through model-based systems engineering. So again, something we heard last session by Nitesh, as well a focus on advanced analysis tools and synthesis of software infrastructure. So that falls under the Cyber Assured Systems Engineering program case at DARPA. As well, I've been focusing on automating the evaluation of software assurance evidence to enable certifiers to rapidly determine that the risk of software deployment is acceptable. And so that work's happening under the Automated Rapid Certification of Software program, ARCOS. Again, that program has really strong ties as well with the last session with FAA, language on safety and security cases, defeaters, et cetera. And lastly, again, these efforts both at NSA and DARPA have provided opportunities for, like-minded collaboration, across, many federal agencies, obviously to include NASA. I'll just stop there.
Okay, thank you, Brad. And I'm seeing like 2 questions on the chat for the moment. They're very focused, but maybe we can make them be addressed by the panel in general. So the first one is to you, Duan, and it's basically about the role, if you've seen basically regulatory failures when you looked at the cases that involve accidents.
Yes, so from the standpoint of when we look at, I'll give an example. Functional hazard assessments, part 25, for example, there's a assumption, through the process that certain failure modes are going to be looked at in terms of a system. And we have seen where systems have been certified, where it's going through the entire process. And when we have an accident, we see a failure mode that should have been considered prior to the aircraft being certified. We've seen it in part 25. We've seen it in part 23 as well. So your transport carrier versus your small airplane. And one may ask the question, how could that happen? But I think the challenge here is when safety engineers, for example, go through the process and the design process to understand the failures, they break down the system functions. But there are still times where a failure mode may be missed. And so when the details or the information is prepared for the regulator, I'm talking during the time frame where we are finding compliance, where the FAA is finding compliance. I think it's important that we take a deep dive into those failure modes, not just what's being presented, but ask the questions that we considered this failure mode and so on. And a lot of that, I think, can help through the safety management system, through safety assurance and the safety risk management function. So yes, we have seen several accidents, some of them I'm working right now as well, where we're seeing software and system related certification issues.
Okay, and I know you don't have control over those standards, so you can only point out the deficiencies there. Since the 3 other panelists are more focused on defense, on the defense side, did you guys see the same type of things in your work, where you see that the regulation is maybe not pushing the people going for a certification in the right direction, or not pushing them hard enough in the right direction? Should I put something on the spot?
I could start you out. I mean, I'm probably going to have the least to say, though, because I'm, very much in the research world. But I have been having discussions with the office here in the Air Force that's responsible for compliance with Section 15, Mill Handbook 516. And, reading over that document, so I don't know what it practically looks like when they have people come and try to do, get things certified. But I do know, looking at the standard, there's just a lot of factors for autonomous systems that are just not really covered in the standard. And you already kind of see this because they get very detailed into the requirements for sort of the flight stability of the aircraft, right? But then when they talk about, say, the human interface, I forget what it says, but it's something like, the human interface has to be appropriate, right? It's I've worked enough with the human factors world to know that it's that's not really very specific, right? So it just seems like they know that they need to be thinking more about revising the standard to handle some of the concerns we already know just with human automation interaction that there's going to be, all kinds of concerns for the interface to avoid things like automation surprises. There's got to be support for sort of data pedigree, for things that are based on machine learning, like just to name a few things. I think we've been talking about they need new methods just because the complexity of the software is becoming too much it's too expensive to get enough coverage through testing. So all that I have seen is that I think the current standards are just not at the point that they're addressing some of the factors we need to address for more automated or autonomous systems.
Okay.
Yeah, I wonder if I could add to that.
Yeah.
One of the differences, one of the key differences, which also I think addresses one of the questions on the board here, is that with the existing standards regulations that require structural coverage, MCDC coverage, of course, for the level A, structural coverage, it doesn't really make sense for a lot of the machine learning black box algorithms because they're running the same code every time. What matters is the inputs. And so we need to be able to develop rules for how we do certification with respect to looking at the inputs to make sure that the system can respond correctly to whatever inputs are encountered in the field. One of the examples was a self-driving vehicle that crashed when there was a white truck against a white sky at a certain angle. So that's the kind of thing that was apparently not covered or somehow slipped through testing. That's the kind of thing that would not be well handled by some of the existing regulations, and we would like to improve on that.
Okay, and then we'll come back because the next question is going to be about testing, and so we'll come back to this. But I want to give a chance to Brad because I don't see him, so I don't know if he wants to react to this.
Sure. Yeah. I guess I was just thinking I might add that in some sense these challenges sort of have these secondary effects, like so the likelihood of initial operational capability in some sense being obsolete out of the box. So these challenges that we're facing could lead to sort of, again, maybe a mission owner's dilemma, if you will, sort of that of accepting of delayed, initial operational capability, as systems increase in complexity, or instead accepting mission waiver limitations. And so, I think that's a trade-off that we want to be able to sort of mitigate and move away from, so that we can provide sort of, again, software certification time, expense, efficacy, that's in line with sort of, modern development practices and processes.
Okay, thanks, Brad. So, like I said, actually the next two questions are about testing. So one is about testing for things like cuts, or even like machine learning software where the access to the code doesn't mean much anyway. So how can we deal with this? And also question about what if the inputs requires long sequences of inputs, for example. So I think the first one that could react to this is Rick, because it was addressed to you, but I think it's relevant to everybody.
Yes. Well, as I was just saying, the existing regulations will certainly need to be extended to handle the autonomous systems, basically the machine learning questions, because they're not well handled currently. So I can't really speak a lot to the FAA regulations, except to say that we need to expand on those. And we are, NIST is looking at this jointly with some others in terms of standards, not necessarily a mandatory standard, but some approaches for assurance of autonomous systems. And so we have begun to address that, and we hope to come out with some recommendations on that in the near future.
So those would be under the form of like coverage, test coverage type of things, or?
That would be part of it, yes. Covering
Okay.
the input space, making sure that we cover the conditions and the factors that might be that might occur in the real world.
Okay. Anybody else wants to react to this question? So that's broadly about the adequacy of testing and maybe what's listed in the compliance, the regulatory side right now. Is that enough? Is that not enough? And maybe we can expand it, like Rick already took it there. Would we need something more or different when we get to autonomous systems?
So to me, it seems like you need something more, because I will say, so for instance, in our multi-UAV or multi-vehicle autonomy framework, it's a service-oriented architecture, and we have all these services. And it's not just about what inputs you give them. They have a very rich state space, right? So for every input they get, they're going to change their state, and then outputs produced in response to subsequent inputs are going to be different depending on sort of the history of inputs that was received. So we did bring up sequences of inputs, right? As you know, something we can use sort of statistical design of test for, but like when you start taking into account sequences of inputs and the fact that the state of the software matters, I mean, you have that combinatorial explosion problem, and I don't think you can actually get sufficient coverage that way, which is why we're starting to try to formally verify the actual behavior of our software services.
Okay. John, any reaction to these questions?
No, I just want to highlight, you know, we're talking about testing earlier, but the verification methods that organizations are using. I think, you know, having to focus on how they're using those methods and the extent of the testing, I think is also important.
Okay, so for you, it's more like in the use of those techniques.
The use, yeah. And then how far are you going to meet the requirement?
Mm-hmm.
You know, it's like it was said earlier about the human factors aspect and meeting the human factors requirements, but there's a time where there needs some specificity in those requirements so that you know, so that the manufacturer knows how to meet those requirements. Because once we pass tests and the aircraft or the system has been deployed, that's when we start to see the issues with the fleet. That's when we start to see the incidents, the accidents. And then we have to go back through the design process and certification to understand why that happened.
Yeah. Okay. Let me do a check with Brad. Brad, anything on the topic?
Really, yeah, nothing more to add, I think, on this question.
Okay. So let me take a look at the. Sorry, I'm reading the question, and that's addressed to Laura. I was reading it to try to summarize it, but maybe I'll read it just out loud. When there is a rich state space and you don't have access to source code, or access is worthless, like in ML, what are your recommendations for how to formally verify it? Just well, like easy question.
Yeah, I mean, I have access to the source code, right? I mean, yeah, for that, I'd have to really, you know, just point to like the research community, and like I try to follow the types of things that they're doing with that, right? So, I mean, with, you know, if you don't have access to the source code, yeah, I'm not really an expert in how to do that. I have seen there are people that, like, from a cybersecurity perspective or a hacking perspective, there are ways to try to back out some of the code into some higher level intermediate language, but I'm going to guess that's not actually a good way to tackle that problem. And you know, for the machine learning, I mean, that's a tough problem, and I think it depends on exactly what you're using machine learning for, because I have seen some approaches that can offer guarantees, but it's under assumptions, right? It's under assumptions that what you're trying to learn has like sort of a well-defined distribution behind it, right? And so when I meet those people and they're working on some of these problems, I say, well, I you know, that makes sense for what you're doing, but I don't know what is the distribution that defines all pictures of cats, right? Like there is no simple distribution for that. So it kind of depends. For some types of machine learning problems, you can find some approaches that have some guarantees, and then for others you can't. And that's where I think you'd have to actually consult an expert on verification of machine learning, you know, to see what they would say about your specific application.
Okay. Anybody wants to react to this question? I know it was for Laura, but.
Well, I think there are some aspects of the machine learning, such as image recognition, where the formal methods haven't been developed yet to really handle what might be needed. So that's, I think, a research question. It's going to be a while before we have that. I wonder if I could also just quickly address the previous one on sequences of inputs. That's one of the things that we developed with the Air Force, looking at efficient ways to do that. And we have some more recent work. So basically, yes, we can address a lot of these problems of exercising deep parts of the code with inputs that will produce the sequence that is needed. And then we also we have an interesting theorem that relates the input space coverage with branch coverage and structural coverage. So we can make arguments and go back and forth between input space coverage and structural coverage that may be valuable down the road in some of these assurance questions.
And are you making I mean, you've talked a lot about the input space and focusing on this, but are you making the connection with the requirements? Like Leon points out that
oh, yes.
a lot of time it goes back to the requirements and actually how well we did a job in covering those and pushing on this. So
that's right. And that's exactly where we want to focus the definition of the input variables that we're concerned about and determine how to compute, how to specify values of those to be used in discrete coverage. So yes, it's very much focused on the requirements. One of the things that we had started looking at recently with the NASA Langley people is maybe there might be a way to go from the FRET specifications to the covering array specifications that we want to be able to generate combinatorial coverage. So that'll be an interesting problem maybe to look at over the summer.
Okay.
I might just jump in.
Yeah, go ahead, Brad.
This is Brad. Yeah, so you know, one of the areas that I think sort of where there's an opportunity to provide, you know, collaboration again, in the sense of, let's say that I just have maybe binary and no source, is again to think about sort of, you know, all the sort of the strong work sort of in vulnerability research. And so at DARPA, you know, I have a program called CHESS, Computers and Humans Exploring Software Security. And obviously the focus of the program is on vulnerability research, you know, vulnerability discovery, but oftentimes, you know, in practice, when I've talked with folks who have to do assessments or reassessments of, you know, national security systems, sometimes they fall into that perspective where they just have, you know, binary. And so, and so it, in some sense, ends up looking a lot like a vulnerability research sort of problem. And so this CHESS program is focused on, you know, developing a system enabling, in this case, sort of both humans and automation to sort of jointly reason over some software artifacts. So it could be over source code, but it's maybe more likely over binaries. And the goal there is in finding vulnerabilities at scale and speed appropriate to, again, the complex software ecosystems, that we're dependent upon within the U.S. government. And so we're combining sort of the strength of both sort of automated program analysis techniques with human knowledge, and so to enhance sort of the security of these deployed systems. And so, for instance, one of the tools that's being developed under that program is out of Arizona State University called Checkers. It's a vulnerability discovery framework, if you will, that integrates automated and human analysis. It helps to sort of unify analysis results from individual analysis, components like, fuzzing or symbolic execution or manual analysis, static analysis, et cetera, and shares, that analysis across components, and then sort of transfers insights from one component into analysis in another component to improve the overall sort of vulnerability discovery progress. And so I think, there's a lot of sort of, I think, rich sort of area and, expertise and tool development that's gone on, within the vulnerability research community that I believe is sort of very ripe sort of for, analysts, evaluators, certifiers that, desire to have, evidence and, to use sort of tools like these sort of in the production of evidence, towards, making some claim about a system. Over.
Okay. All right. I'm going to skip the question that puts you on the spot to one about using formal methods at NTSB, because I think we know the answer to that, and that's not really one that's so relevant. But we've been dancing around the topic of new technology like ML and those kind of things for autonomous systems. And I'd like us to spend a little time on what are your thoughts about addressing this? Are we or do you have any effort to try to influence the regulatory side for this, like influences in or plan to influence standards around the assurance of those systems? And maybe we can also talk about how, as us government agencies could collaborate better to try to cover more in that space, since it's the next big frontier that we're going to see. And Duan, I don't know, have you guys seen already accidents related to this type of technology? Probably not, right?
No, it's, but I wanted to highlight something that you were saying about the assurance side. Through the investigative process, NTSB does develop recommendations. And a lot of those recommendations are built based off of a lot of the findings in our investigations and so on. So that is a space where we can influence in terms of the recommendations to the FAA from that standpoint. Okay.
The scar tissue that Natasha, building on the scar tissue that Natasha was talking about in the previous panel, I guess. All right. So going back to those techniques, to the systems are going to be new, like autonomy, and everybody is kind of centering it around ML, but they're like more like different techniques that can be used in ML for the systems. Do you have planned efforts in this? I know, Brad, there are some with the Assured Autonomy program, at least on your side. And maybe Laura, you can talk about some of the efforts you guys have around that.
Do you want me to go first or Brad to go first?
Go ahead.
Okay. Yeah, that's Guillaume, the point you brought up that not all AI has to be done through machine learning is something I also have to raise a lot, because I think a lot of people at the Air Force anyway, they're very interested in solving the perception problem, right? And that is very ML heavy. But we have a lot of work here designing controllers for teams of UAVs that are based on other types of formalisms like Markov decision processes and partially observable Markov decision processes that are difficult to analyze. Like the complexity of these is very high, but they are analyzable. And I also have some work going on. You guys have some similar work where we will develop some algorithm. It's got some very complex decision logic, and maybe you have some assumptions in your environment, and you develop a proof that this decision algorithm is correct relative to some rich specification. But as the algorithms become harder, those proofs become harder, and you start to risk the proofs actually being wrong. So one of the things we're working on is we have an algorithm that's implemented in OpenUXAS for distributing surveillance of a parameter in a decentralized way among a team of UAVs. And there's a paper that goes along with that, and it like argues the correctness of the algorithm with sort of paper and pencil proofs. And what was interesting was we had someone that was interested in like, could their formal methods tool actually handle formalizing and then proving the correctness of this algorithm, and it actually found a counterexample to one of the lemmas in the proof. And so it's kind of this happens sometimes, right, where you have a paper and pencil proof and it turns out that it's not actually correct. And so the thing with that algorithm is that this proof was on the bound on the time of convergence. And so we technically don't even know, whether or not it converges. We think it does, but we're actually still working on a proof. It's actually turns out to be the reason the proof was wrong in the first place is it's a very simple algorithm, but reasoning about it is very, very hard. And so we're still working on that. We think we're hopeful that we will get to a proof eventually, but we are using some theorem provers to try to help us develop that proof.
Okay.
Sorry, I went a little off on a tangent there.
No. That was on topic. Brad, you wanted to react to?
Yeah. So there's sort of numerous programs at DARPA with an I2O around thinking about autonomy. And so the one that you mentioned was Assured Autonomy. Sandeep Nima is the PM for that program. And it's focused on creating capabilities, technology for the continual assurance of the term that's used is sort of learning enabled cyber physical systems, where he sort of defines continual assurance as assurance of the safety and functional correctness of the system provided at design time and continually monitored, updated and evaluated at the time as the system and its environment evolves. So there's that program. There's again sort of several others sort of within the DARPA purview. For myself, sort of at NSA within the research directorate there, I had sort of several programs focused in a couple areas. Sort of one was again thinking about the assurance, again, which is the point of the topic here, sort of AI machine learning systems and methods, and then as well sort of thinking about the application of AI and machine learning in regard to advancing cybersecurity. And some of those programs involve the application of formal methods as well. One other thing I was just going to mention was that within the initial question you asked, or we're making a question about sort of engaging with one another. And so one thing that I would just mention is one of the sort of coordination groups that I've been involved with for a couple decades sort of has a role sort of in this, I think, as well, which is the NIDR-D, sort of networking IT R&D. They have an AI interagency working group. And that group sort of seeks to provide for coordination of federal AI R&D. And so they're seeking to sort of advance the mission of the National AI Initiative Office. And they put out a strategic plan for AI R&D. And some of the priorities sort of from that community, which I think, again, could be sort of activities for, again, this community to also sort of, be a part of and to join in, have to do with sort of, the coordination of, long-term federal investments. It's just sort of at the core, sort of something that's, I think, valuable to do, but also sort of thinking about the development of shared public data sets and environments, providing sort of for measurement and evaluation of AI technologies, expanding that sort of AI workforce through education and training. And then I think also sort of facilitating sort of public-private partnerships. And so there are more sort of strategic priorities sort of that are within that plan. But again, those are a few of those. And so I think that's, one aspect where, a group focus sort of in AI sort of from the federal perspective, are thinking about, how might we sort of engage with one another to get sort of, strong results. Over.
Yeah, and it seems that they're like very, very different efforts. I mean, Laura and I had that discussion at dinner the other day about, I was telling her about a group in the defense, largely DoD realm, that I got involved with, that was doing T&E or investigating T&E for autonomous systems. And she told me that, oh, that's one of them that she's aware of. And then like, it seems that everybody's starting its own little group, and we probably would be better off trying to coordinate a little more on this. Maybe neither of these should there to drive this. And on a follow-up question, Brad, there was a question really for you, and was about, we mentioned assured autonomy, and I think it's about to end. Somebody is asking if there are upcoming BAAs from DARPA in that realm.
So I know that there definitely are. I don't know what I can say sort of currently about that. It's sort of a program that I've initiated, and so I don't know where it's at sort of going forward, but it'll sort of build off of, again, some of the work that Sandeep has been doing through sort of the Assured Autonomy program and other programs. And so that it's definitely the case. So I think be on the lookout for announcements that are, I guess, currently sort of tied to Sandeep Nema. And you're right, sort of Assured Autonomy, I think, has maybe another 6 or 9 months, something like that. It's I think has a lot of focus sort of going forward, sort of into applications and tech transfer and things like that. But again, still an active program producing strong capabilities, but more sort of on the way from DARPA I2O in that space.
Okay, thank you, Brad. I know it's difficult to talk about the upcoming ones. There are blackout periods and all those things. So I would say they should monitor the DARPA sites for the upcoming BAs.
That's correct.
Very focused question for like some of our panelists, and one is for you, Duan. Some people are asking, and I know I want to bring up that question because I had that question for Dana before. Some people are asking if there's a single place where they can find a list of the incidents that have been analyzed by NTSB and the recommendations to get probably directions on where to take the research.
Yeah, there's a system that's a pretty new system called Carol database, so CAROL. But it basically, if you type that into the website, you'll see on ntsb.gov. But it will take you through pretty much every case that we have investigated. And then on that same page is a recommendations tab as well that goes into that talks about some of the recommendations that we've completed. So yeah, it's a rather new database. It's been refined, if you will, but it's Carol, CAROL.
Okay, thank you, Duan. Another pointed question for you, Laura, before I ask for your concluding statements. So somebody's asking what theorem provers you're using, and especially in the context of reasoning about the perimeter surveillance.
Yeah, so I should not claim so much personal credit for that problem. A lot of the work, so the work was in collaboration with Collins Aerospace. So originally when we started that effort, they wanted to see if they could apply the Agree model checker to our problem. So we basically helped them like understand our protocol and the algorithm and formalize it in Agree. It's okay, and then so we found the counterexample, and then we said, okay, how do we come up with a proof? And then it was really David Grieve at Collins Aerospace that came up with a proof approach in ACL2, although we also got some interested people from CMU who were working with the lean theorem prover. And so I met Jeremy Avogad at a conference, and I had presented on this, the fact that we found this counterexample in Agree. And he's like, oh, this problem looks easy. Like he's like, oh, maybe some weekend I'll formalize this in lean and I'll find a proof for it. And then he comes back to me like a year later and he says, this problem is evil. It looks like so easy. And it's like, he's like, I can't prove anything about it. And it was David Grieve who came up with a very sophisticated proof approach, and then Jeremy Avogad and then one of his students eventually came back and said, okay, we think we have an easier approach for part of this problem, not in the model, not in a theorem prover, but then David Grieve formalized that in ACL2, and he recently presented on that at the ACL2 workshop that was, I think, last month. So there's your answer to that. What makes the problem hard? So, and this is a very simple version of a case like this where we have these UAVs and they're moving in a continuous space. And here we assume that a parameter, it's anything that you can map to a line. So anything that's isomorphic to a line, which is a lot of things. But we ultimately end up modeling this as UAVs are moving along a line. And so you've got that, continuous component of the space, and that's infinite. And then they're learning. I say learning. They're observing things online, so they don't know when they start off how many other UAVs are on the team, where are the endpoints of the perimeter. They've got to discover those things as they encounter them, and we assume that they're very communication limited, so that the UAVs can only exchange information essentially when they're co-located. So you've got this challenge that you're trying to reason about, like, they start off with incorrect information. At some point, they get correct information. They're constantly moving. When they meet each other, they have to exchange information and then make decisions about where to go and split apart in order to try to achieve this even distribution of the parameter. So you have this, infinite state space because of the continuous part. You've got a lot of different discrete decisions that are kind of highly discontinuous over this continuous space. And then you've kind of got these two behaviors going on at the same time where they're information gathering, but then they're also trying to converge to this even distribution. So the original proof approach actually tried to split those behaviors apart and kind of reason about a worst case. And that's actually where the problem was, is that you can't split them apart. It actually affects, both behaviors affect each other. So that's the brief overview, but we do have publications on that if you wanted to read about that in detail.
Okay. If you put that in the chat, if you have a link to those and you can put that in the chat, I'll make sure it makes it to the questions as an answer.
Sure.
All right. We're almost out of time, so I'm going to do a last round for concluding remarks. Since I started with you, I'll finish with you, Laura. I'll start in the reverse order this time. Then Brad, any concluding remarks?
Sure. I guess one thing I would also just mention on that last point was, and it ties into sort of, I guess some discussion sort of we've had around AI, is that I also have sort of an AI sort of exploration at DARPA that I've started, which is, it's called PEARLS, Proof Engineering, Adaption, Repair, and Learning for Software. And so it's a program sort of focused on exploring the use of AI and machine learning to support and, possible automate the generation and maintenance of proofs used in formal verification of software. So, you might take a look at that. Sort of again, the program name is called PEARLS, and it's just sort of something that's gotten underway. But as a closing statement, I guess for me, I think there's definitely sort of a desire to sort of focus on evidence. and sort of accelerate the development and adoption of composable sort of evidence-based approaches to support confident assessments of vulnerability, sort of making use of sort of direct evidence. And then taking that next step, there's that focus on assessment, sort of improving methods for measuring, modeling, and assessing cyber risk for systems and their elements, and integrating sort of cyber risk models into that body of evidence. And then lastly, a focus on practice, enabling sort of acquisition and engineering practices that support, pipelined acquisition and assurance for the rapid delivery of increments of capability with ongoing evaluation in support of, confident risk assessments. So, evidence, assessment, and practice, I think, are sort of three sort of, themes and threads that, I like to sort of push on. And I'll close there.
Okay, thank you, Brad. Rick?
I'll just reiterate some of the points I'd made before, which is that autonomous systems assurance is the real challenge right now. We should be able to do that with respect to safety, but we shouldn't forget security while we're doing that, even though that's a much harder problem. And the way to do that is focus on the input space.
Okay. Thank you, Rick. Duan, any concluding remarks?
Yes. So from my standpoint, closing the comment, certification, aircraft certification is very important. And when we start to, we're getting into, complex integrated systems nowadays. And I think that we need to understand a little bit more about the system and its operational capability, and also the safety assessments. Probability and severity are very important, and you see that in a lot of safety analysis is the use of probability and severity. And in the development of an aircraft and related systems, I think we have to have a laser focus on some of the corner cases that we don't know about, because NTSB sees this in aircraft accidents later on. But if we can somehow, in the requirements phase, when engineers are looking at system and subsystem requirements, and even some of the verification methods, maybe there's a way to find out some of these issues during, say, testing, laboratory testing, or aircraft testing. So we're aware of these, and the industry or manufacturers can make changes to the design prior to deployment of the system. That way, when we get into a situation where something doesn't pass a test, or there are problems with the testing, it can be done at that point in time, not when the system is deployed, and we find these later. So I would say certification efforts are important, and from an NTSB standpoint, we are looking at that in investigative activities.
Okay, sounds good. Thank you, Laura.
Yeah, so I just want to say I'm really glad that you're hosting these type of events to bring lots of different organizations and people with different backgrounds together, because I know, just the question I got today, like, I'm always frustrated that I don't know more. There's just so many different things that you have to consider if you need to verify, complex or autonomous systems, right? I'm not an expert in statistical analysis of tests. Like, I'm not an expert in machine learning. I do some human factors, but I never do it alone because, I don't have I have to, collaborate with people on that. So there's so many different areas that we need to bring together for this. And I also just wanted to express to NASA my appreciation for all the work you've done in formal verification, because it is very helpful for me to be able to point to things like your work on Daedalus and the compact position reporting algorithm, and some of the tools that you've developed to try to convince people at the Air Force that, yes, there are realistic problems that we can tackle with some of these approaches. So thank you for that.
Thank you, Laura. And I didn't ask her to say that. But thank you to all the panelists, and I love my own conclusions. And it reminds me that we all should talk more often. Like you just said, Laura, it's always extremely useful for us to confront our point of views and make sure that we don't forget things that are important that we might have missed. So thank you again for attending this panel. And I think I'm gonna kick it back to Joe because there's a Q&A following this, right, Joe?
There is a Q&A. I see that. Well, first of all, the question people have asked, what happens to some of the questions that were up here? I understand that the system, when a question's answered, it archives it. They'll show up at the end of the day, so that what we're seeing here are the questions that are unanswered. Right now, I think we've addressed all the questions that have been asked. At the end of the day, there's an opportunity to think of other ones to ask the project team, some of the key moderators that are still with us. Period of time right now, while people are thinking of what their questions may be, I'd like to jump to the agenda if possible, and go over what we'll cover tomorrow. We're going to start just a little bit earlier tomorrow, about 5 minutes earlier, with welcome and logistics, so that Cheryl Quinn, the Deputy Director of the Aviation Safety Program, can speak with us and give us some opening remarks. And then we're going to have 3 panels. We'll start with the academic perspective with Dr. Terry Morris, and be interesting to hear what they think about training students, training the next generation. We heard earlier that there was concerns about the ability to use these complicated techniques, and we know that our academic collaborators, they do research, but they're training the next generation of researchers. Then we're going to hear industry perspectives, industry that does the research. It also looks at and applies some of our tools on their use cases and problems. That'll be led by Dr. Paul Miner. And then finally, Dr. Misty Davies is going to be part of a panel, leading a panel. It's going to talk about the future challenges and solutions. So this is where we start looking at, in our vocabulary, TC4, or the V&V and certification of adaptive AI type methods, non-traditional methods. And so that will be the last of the 3 panels tomorrow. And then we'll have a final Q&A and closing. So want to thank everyone today for attending. Let's see what kind of questions we have. Do we have any new ones, or are they look like they've all been addressed with moderator
So
answers?
far, we haven't gotten any new ones in, Joe. I'm making them all public. Anything that you see that doesn't have a moderator,
Right.
oh, yeah, some of the newest questions were all covered, so.
All right, so it's our intention to, for those that we don't address right now or at the panel, to do them offline, talk to people, and try to get our best answer for those, so that at the end of this meeting we'll have addressed everything that people have asked.
Absolutely. A lot of these questions were answered by moderators already, so please feel free to go back into Conferences.io and check it out. For those of you who have asked questions but they were not covered, I've included my email address. I'm happy to forward your questions to our team and get them answered for you.
Well, thank you, Abigail. Pleasure working with you on this, and with the organization that you and your NARA team provide us. Really appreciate it. And thank you for everyone for attending today. I'd like to close by thanking the moderators, the panel participants, everyone that helped make this successful first day of our meeting. Again, I'll look forward to seeing everyone tomorrow about 8:55 for a brief introduction, and then Cheryl's introductory talk at 9 o'clock Pacific time sharp. For those on the East Coast, of course, it's 12 noon. Thank you again, everyone. Have a good rest of the day, afternoon.